Perfect. Hello, everyone, and welcome to the second edition of the Lifelong Learning and Personalization in Long-Term Human-Robot Interaction workshop at the International Conference on Human-Robot Interaction, where we make a leap from the traditional one-size-fits-all approaches towards adaptive robots of the future. I'm Bahar Irfan, and I'm the coordinator of this workshop series. I'm a research and development associate at Evinox Service Equipment Industry and Commerce Incorporation. I was also briefly at Disney Research. I have a diverse background in robotics, from personalization in long-term human-robot interaction during my PhD at the University of Plymouth and SoftBank Robotics Europe, to user-centered test planning for household robotics during my master's in computer engineering, and for building robots during my bachelor's in mechanical engineering. Overall, my research focuses on creating personal robots that can continue to learn and adapt to help people in their everyday lives. And I'm co-organizing this workshop with amazing people. First of all, we have Aditi Ramachandran, who's our publication chair, and she's also the Chief Robot Officer at Venn Robotics, where she works on building education robots and oversees all software development at the company. She received a PhD from the Social Robotics Lab at Yale University, where her research focused on personalized social robots for tutors for children. Sam Spaulding is our web chair and a PhD student in the Personal Robots group at the MIT Media Lab. His research focuses on building robots that can learn personalized, cognitive, and effective models of users on repeated interactions and across different tasks. Herman Parisi is the program director of artificial intelligence at IBM Data and AI in Mountain View, California. He's also the co-founder of Continual AI, which is a group focused on continual learning in machine learning. He received his PhD in computer science from the University of Hamburg, and he was a visiting researcher at the Korea Advanced Institute of Science and Technology. His main research interests include human-robot interaction, continual robot learning, and neural-inspired AI. And finally, we have Hatice Ganesh, who's a professor of effective intelligence and robotics, shortly AFAR, and the head of the AFAR lab at the University of Cambridge's Department of Computer Science and Technology. Her expertise is in the areas of effective computing and social signal processing, cross-fertilizing research in multimodal interaction, computer vision, signal processing, machine learning, and social robotics. We previously organized workshops at HRI and Roman. I strongly recommend you to check out the recording from last year's workshop, which is available on our website, as well as the proceedings from these workshops and the groundbreaking research at the Frontiers in Robotics and AI journal on this research topic. Throughout this workshop, we'll have several talks focusing on lifelong learning or personalization. And our first keynote is Professor Ginevra Castellano from Uppsala University, who will talk about personalized interactions in social assistive scenarios, as chaired by Hatice. And we'll continue with two full paper accepted papers on personalized robot-assisted therapy in autism, as chaired by Sam. Each of these talks will last 7 minutes, and there will be a 3 minutes Q&A session. Then Herman will break us into small groups for the breakout session, where we will briefly introduce yourself and your research to get to know other researchers working in these areas. After that, and a short coffee break, we'll come back with Aditi introducing our second keynote speaker, Vincenzo Lomonaco from University of Pisa, and also co-founder of Continual AI and AI for People, who will be talking about the continual learning in distributed robotics intelligence. After that, we'll continue with the lifelong learning papers on reinforcement learning and imitation learning, as well as a paper on, as a talk on personalized robot coach for sports training. After that, we'll go back to our breakout rooms at the beginning to talk about the robots from science fiction, how we can apply them to reality and when we'll be able to see them. And for the grand finale, we'll have a panel of experts from industry and academia, Natasha Jack, Samuel Barrett, Benjamin Bushfield, Kate Darling, and Kirsten Daughtonen, which will be moderated by me. And the session will be chaired by Sam for the audience questions. If you're wondering our take on these topics, I previously gave a tech talk at the Software Robotics Europe Heart webinar on the challenges and suggestions on these areas. You can watch online on YouTube. Sam is giving a talk next week on lifelong personalization for social language in literacy companions that you can watch for free by registering for his talk at Talking Robotics. And if you're working on these areas and wondering where to submit your work, we have few venues that might be interest to you. First of all, we have a workshop on continual learning in computer vision that's co-hosted and co-organized by our second keynote speaker, Vincenzo Lomonaco. And they have a deadline pretty soon in 2 days. But they also have object recognition challenge from March to May that may interest you if you're working in continual learning in these areas. And they're not only accepting computer vision papers as well. I'm also co-organizing a special session on short and long-term personalization in human-robot interaction at Roman that has a deadline next week for full papers. And there's another workshop coming on these topics, especially focusing on the effective computing at Roman. So stay tuned for that. The other venues that may interest you are conference on lifelong learning agents that also has a deadline this week, and conference on robot learning, CORL, which has a deadline in June. So you have plenty of time to work for that. Now, before I leave the floor to Hatice, I would like to remind you to turn off your cameras and mute yourselves during the talks and turn them on for when you're speaking or you're presenting or when you're asking a question, and also for the breakout sessions so we can have engaging discussions. And the workshop is being recorded, and the recording will be available after the workshop on the workshop website. With that, I would like to tell you, we all hope that you'll be enjoying our workshop, and I'm leaving the floor to Hatice for our first keynote speaker. Hatice, are you here? If Hatice is not here, I can, or Sam, could you present our next speaker?
Yes, hi everyone. Yes, so I am happy to introduce our first keynote speaker. That is going to be Ginevra Castellano, and she is a professor in intelligent interactive systems at Uppsala University. She leads the Uppsala Social Robotics Lab. She has research interests in the areas of social robotics, HRI, social learning, personalized robots, multimodal behaviors, and robot ethics. She's coordinated a number of large-scale EU FP7 projects, including the Horizon 2020 Animatus project, the COIN project, and she's also an associate editor of that Frontiers in Robotics and AI topic that we mentioned earlier. She's done a lot of great work in this area, and we're very excited to hear her give a keynote for us.
Well, hi everyone, and thank you very much for the introduction. I will now share my slides. And nice to be here. Thank you for inviting me to this workshop. And in today's talk, I'm going to present some of my work on personalized human interaction in socially assistive scenarios. So as the title suggests, most of my work focuses on developing thoughts in socially assistive roles, primarily work in applications in the domain of education, entertainment, and more recently that I work with socially assistive scenarios where robots a socially supportive role, not necessarily in isolation without the extension to physical support to human, but the main focus is developing social skills for robots to provide social support to humans in different scenarios. So I primarily interested in two main strands when I develop socially assistive robots in these scenarios. I'm interested in robots' appearances and embodiments, and the extent of human likeness that it's needed in different contexts in order to support useful interaction for human users. On the other hand, a lot of my work is also focused on designing and developing socially appropriate behavior, and that involves developing social behaviors that are appropriate to the context of the interaction. And for this, I use a range of many different methods, included but not only limited to machine learning. And I will discuss today some of these in the context of personalization. So human-like social appearance, social behavior in the context of socially assistive scenarios to promote and support humans and to promote human flourishing. That's the overall background and motivation of my work. But we know that, like all technologies, robots may not only bring benefits, but also change how we think and behave. And there's a lot of questions, especially recent ethics, on the need of ethical AI and robotics and trustworthy AI robotics. And what we know is that technology is already changing us. The information society and these are more and more ubiquitous, and so in the internet, and this to have all the information they need wherever we are. So that's a massive change compared to 10, 15 years ago only. Even with social media, we are more connected with each other in many ways. But we also know of social interaction. We have grown to each other, but in some ways also further apart. So there's a lot that is happening with many different kinds of technologies out there, and we need to ask ourselves, what serves us best. So compare social robots with some of body with human-like characteristics, and that means that have a higher agency and possibly higher possibility to change how we think and behave in interaction with them. The recently published EU guidelines for trustworthy AI warn of the need to study the social impact of AI systems integrated in all areas of our lives. And AI systems can impact social relationships and so this calls for human-robot interaction researchers to design and develop more human-centric and trustworthy artificial intelligence and robotics. Which robots adapt the way to communicate in the world and the other way around. So this means really robots that anthropomorphic, not only in how they look, in their appearance, but also in how they behave. So then how can we build human-centric, personalized human-robot interactions? So the key topic of this workshop is personalization, and I like this very much in the context of building human technologies and robotics that is trustworthy. So that's the first question I want to start with. And I will give some examples of work on personalization that I have done in different kinds of social assistive scenarios. So I will start with the topic-based personalization. This is my first work in the area of personalization, which I have started over 10 years ago. And in the context of a European funded project called LEAP-HRI, which aimed to build robotic companions that were able to engage human users over extended periods of time. So long-term interactions. And at the time, it was still a new concept of what does it mean to study long-term interaction. So in the context of this project, and in collaboration with the technical university of Lisbon, including Anna Paiva and Yolande, we designed a robot chest with children. So you see here in the picture an iCat robot, LEAP's iCat, that plays chess with children to an electronic chessboard. So what the basic characteristic of these scenarios are is that the robot can at any time what happens on the chessboard. So you can monitor the state of the game, the progress during the game, and who is doing what. And the robot can also emotional facial expressions. So what we wanted to do, we wanted to add to these basic capabilities and design empathy-based personalization in this robot. But first, let's discuss a little bit about empathy and why empathy. And there are many definitions of empathy out there. So the one that so we took into consideration is one by Kaufman, according to which empathy is an active response, which is more appropriate to someone else's situation than one's own. And in the context of social robotics and in the context of building companion, the key aspect of empathy is, I think, is a prerequisite for providing social, emotional support, and also enable the to sustain and use over extended periods of time. Because the aim was to build robots capable of interacting successfully and keep users engaged beyond the single short-term interaction. So the idea was to work on personalization with each specific child user in mind, by giving the robot the ability to create an affective, on one hand, the ability for the robot to infer the user's active state by means of monitoring the state of the game, but also monitoring the verbal behavior displayed, so perception of the user on one hand, and then based on perception and developing the capability for the robot to respond in a way that is contingent to this state. In this sense, we talk about because we perceive affect, we interpret, and also we respond with an effective, empathic. And this is the model that we built. So again, the idea is that we monitor the affective states of the users. Whenever children are experiencing negative feelings, the robot intervenes and generates supportive behaviors by means of speech utterances, also keeping track of past interactions. And these behaviors are supposedly going to be adapted for specific users, but let's see how. First of all, here is an example of what we call support behavior. We adopted a framework et al. And investigate four main category of social support. So the robot had at disposal a pool of supportive behaviors, a pool of different utterances, different types for every type of support. We have the category of information support. The robot could ask if help was needed or suggest something specific at the level of the game. Or we could have example of tangible assistance. For example, the robot could deliberately play a bad move or suggest a good move. And we also then worked with the esteem support, An example here is, well done, you play what I have played, or don't worry, you didn't have better options, or even emotional support. An example could be, I understand how you're feeling, I've been through similar situations. So these are examples of the pool of supportive behaviors that the robot had. How we choose which behavior to play, and how does personalization really work? Approach. So it's a policy learning problem. The online learns what behaviors are most effective for specific users. So the idea is to support and instruction to achieve personalized interactions, which is quality of interaction. So in order to test the effect of behaviors and to select more often some of these over time, monitor the user state before and after the robot plays this behavior. Evaluate the model, this personalization model in real-world environment. We conducted a 5-week study in a primary school with 16 in a school. And at the end of action, we used questionnaires to ask questions to children in terms of perceived social engagement and changed over time. And what we found is that the ratings of all of these variables remain similar after 5 weeks. And this was contrary to initial results that we obtained in exploratory study. A robot that was not endowed with it to decrease levels of engagements, for example. So the key message is here that the personalization over an extended period of a week worked in the sense that it was able to maintain engaged for the whole time. After a number of years, I came back to work again on personalization, this time in the context of robot-supported learning. In the context of a project funded by the Swedish Foundation for Strategic Research, where we want to explore personalization in order to give the robot a robot the ability to optimize achieve in educational settings. So we're still interested in understanding how supportive behaviors employed by the robot can be learned and adapted to a specific user over time, but this time aim to maximize the user's learning performance in learning. But while still interested in the interaction quality, for example, user engagement. So we built a scenario where a pepper robot acts as a tutor and helps learn how to solve grid-based logic puzzles like nonograms. And here again, the robot learns a user model based on the interaction process and generates verbal utterances in order to provide social support during learning. And that happens whenever the robot the user is experiencing difficulties. So again, similar to the previous work, we treat this as a policy learning problem, and we work with reinforcement learning and adopt an approach which learns over time supportive behaviors maximize the user's task performance and, on one hand, and positive reactions to the robot interventions. So we ask users to give positive verbal feedback to the robot if they appreciate the robot's interventions. And as you see here on the bottom right, we focus on the type of supportive behaviors that are suggested by Cutrone et al., which we also used in the context of the ICAT robot, just adapted to this, this scenario. So in this case, we conduct a user study with 2 participants where we compare 2 groups. So we had one group of participants interacting with a robot, which was able to personalize into each individual user in the way that I have explained. And then also a group that which we call random adaptive, where there's no personalization, basically, and the behaviors are random. And these are the 2 questions that we asked during the study. So first of all, does personalization improves oral task performance? And second, is robot more effective than a robot that adapts to its user without personalizing? The time taken to complete the decreases over the tutoring sessions for both groups. And we also found that participants are more efficient at solving logic puzzles for a robot that exhibits more varied robot behaviors compared to a robot that personalizes its behavior by converging on a specific time. And what this means, in short, is, contrary to our expectations, the group that interacted with the personalized robot liked the robot less and also was efficient, which was interesting, but not completely unexplainable. In fact, with results are in line with previous work that show that a robot that is too social and adaptive may not lead to increased learning scenario. We find that more work is needed to understand the implications of personalization with both a social and a task component. So in components at play. If we, for example, remember that with the ICAT robot was a task component there too, but when it came to personalization, the robot's model did not take into account the state of the game when choosing the social supportive behavior that the robot displays. So social and task-based scenarios are always tricky to balance. And also there's also a component of choice of the algorithm versus the interaction design. We think that what matters here is not only the choice of the learning algorithm, but also the interaction design when it comes, for example, to designing ways to use users' feedback for the robot to learn how to behave. If we think about the example of the ICAT robot, the user's feedback was really, we track the user states, and we use that information to adapt the behavior of the robot here. And the role of the user is a little bit more extended. Users that they have the opportunity to feedback to what the robot says. So this is very much an area that brings together both robot learning and human-robot interaction designs. Now, so far, I have presented 2 examples of personalizations based on robot learning and reinforcement learning framework. but also other factors affecting personalization, which be really important to take into account, especially when we have as our objective to develop robots that are able to engage users over. So one of these factors is robot appearance. So I want to take some time to present a different kinds of which highlights some other factors that could be interesting to take into account when thinking about the personalization. But first of all, on the importance of appearance, we know the literature that people tend to anthropomorphize robots to attribute them human characteristics. And we also know that people experience empathic concern even for non-anthropomorphic robots. Other results, however, suggest that the more human-like a robot is in appearance, the more likely people are to empathize with it. People's responses changes, though, in presence of very human-like robots, such as androids. According to the uncanny valley hypothesis, human responses to a human-like abrupt shift from empathy to revulsion as the robot approached but failed to attain a lifelike appearance. So one question of interest here is, does perception of a robot's uncanniness change over time? Because most previous work has investigated perception of uncanniness in very short encounters with robots. Much less is known instead about whether and how perception of uncanniness changes over time. So that's also important when we're interested in modeling long-term interactions. So for this reason, we conducted a study to investigate repeated interactions to influence the perception of uncanniness and, more in general, the perception of a social robot. So a key question here is, are first impressions good predictors of long-term perceptions of robots? And we know that, we know from the literature that in zero acquaintance context, which are situations in which we are confronted with previously unknown persons, we make judgments within a few milliseconds. And we also know that humans form impressions of another person based on the first 5 minutes of the interaction. And several studies, psychologists have shown that familiarization across repeated interaction improves people's perception of the other. And that the more we become familiar with someone, unless we develop interpersonal conflicts, bored or disgusted. But even how these findings relate to human-robot interaction is not well understood yet, even though this knowledge is quite crucial when pursuing long-term interaction. So we don't know if first impressions may or may not be good predictors of the future relationship with the robot. But let's take a look at the scenarios which we developed to investigate these questions.
In this demonstration, we introduce a pedagogical reference resolution game, serving as a engaging scenario to study repeated interactions with a social robot. The cooperative game we developed is designed to enhance people's geographic literacy when playing with a robot team partner. The players have the role of the tutor in this scenario. On the iPad, they see the world map with one country highlighted as the target. Their goal is to get the robot to select the same country on the shared screen, which is placed in between the two. The robot thus acts as a learner in the pedagogical game. Any verbal description, including the use of the country's name, is allowed to identify the target. The goal for the human-robot team is to score as many points as possible during the 10 minutes of game interaction.
So it's to the east of India and north of Australia.
Got it.
You got it.
Is it this one?
Yep, that's the one. Good job.
Nice.
So, should we take the next one?
Yes. Let's move on.
Alright, you remember where India was?
Yes.
So this country is bordering to India to the west of it.
Is it this one?
Yes, that's the one.
Yay!
Good.
We use the blended robot head fur hat as a robot platform for playing the game. The appearance of the robot can easily be changed by applying a different facial texture, making the robot look human-like, mechanical, or like a morph between the human-like and mechanical version, among others. The robot is teleoperated according to a Wizard of Oz protocol by a researcher trained during 50 online game interactions. Before and after the game, participants engage in a brief social chat with the teleoperated robot.
Hi, I'm Neil. What's your name?
Sophia?
Awesome. Nice to meet you. Well, I guess we get to play a game with each other. That sounds pretty nice, don't you think?
So we use this geography literacy cooperative game as a scenario to study repeated interaction with the social robots. And we conducted a user study with 49 participants and who were asked to play this game with the fur hat robot. We measure how their perception of the robot changes over 3 sessions with 3 to 10 days of 0 exposures in between. And then we measure perception of the robot across a set of perceptual dimensions, including anthropomorphism, competence, likability, and threat. We found that repeated interactions have an overall positive effect on people's perception of the robot. And the results show that different perceptual dimensions evolve differently over time, but in a similar way for all robots' appearances. And the robot's competence, which is displayed here, is the fastest to stabilize, as it does not significantly changes after the first impression. Then we found that repeated interactions increased people's perception of the robot's anthropomorphism, which stabilized after the first interaction. Participants liked the robot better the second time they interacted with it. And finally, perceived threat decreased over the 3 sessions. So the findings suggest that our mental image of a robot is built over time, and that perceptual dimensions that contribute to it stabilize at different moments, with the robot's competence being the fastest to stabilize and perceived threat the most fluctuating over time, as we can see in this graph. So in summary, what we find in this study is that by assessing perception of a robot at different moments, perceptual dimensions evolve differently over time. And we also found evidence that initial biases towards the robot do not wear out over time, which is something that strengthens the importance of a robot's visual design. So then a question here, so how do we consider people's perception of robot in personalization efforts? If we find that by studying repeated interactions, it is pretty clear that perception of robot varies in different ways over time. So this is perhaps a contextual factor that's worth considering when thinking about ways to design personalization for robots to work over extended interaction, so beyond a single short-term interaction. So when we think about perception of the robot, this is clearly something that we expect to affect the behavior of the robot. So think about the user's social interaction with the robot, the user's affect, which is something that we have considered earlier, the user's engagement. So there are a lot of behavioral aspects that we expect will be affected by people's perception of robots, which I think it's a contextual factor worth to be taken into account. And finally, I want to end this presentation with another example of personalization. So far we have talked about personalization in terms of real-time adaptation to a specific user, primarily by using robot learning frameworks. Then we reflected on the fact that there may be contextual factors. I just talked about this, the people's perception of robots that might be important to consider in the modeling. But now personalization could also mean to adapt not only to a specific human user, but a category of users. So I want to talk today about some initial work that I have done on gender-sensitive design of social robots. So one of the research areas that I have recently started to investigate is socially assistive robotics for women's mental health care, and specifically how to design and develop robots that can support clinicians in the diagnosis of peripartum depression, which can have a high incidence during pregnancy and after childbirth. So this is a new project which is funded by a research center on women's mental health at Uppsala University. So a key challenge in this context, in the context of diagnosis and screening of peripartum depression, is that access to skilled personnel with training to perform interviews in primary care can vary substantially and also lead to high waiting times or to a regular interview of low diagnostic accuracy. So we're interested in exploring how social robots may be used to assist clinicians in interviews. But I mentioned earlier the recent EU ethics guidelines for trustworthy AI. And I also mentioned that they identify a set of requirements to achieve AI that is lawful, that is ethical and robust. And I also mentioned that robots are a type of AI system. So if we think specifically about this application, so we're clearly dealing with the vulnerable population. So it becomes really extremely important to think about how to involve patients, how to involve clinicians in the design of such a robot. And the role that the robot will have and how it should help clinicians in the interview process. So in this specific context, we're interested in the aspect of fairness, so as a requirement for trustworthy human-robot interaction, specifically of gender fairness, since in this scenario, we're working with pregnant women. So the question is whether and how we can conduct a gender-sensitive design of social robots in this context. And this is a project which is highly interdisciplinary. And I want to give a very short introduction of the work we have done, and I will not talk about many details because this is work that is going to be presented during the night at LEAP-HRI, so between today and tomorrow. Yeah, if you have the possibility, maybe not to be up at night, but to watch the video afterwards, you will find more details about this work there. But very shortly, I want to make a connection here with personalization. So what we have done, so we put together a team of researchers with competencies in both human-robot interaction and sociology of law. And we have conducted interviews with experts in peripartum depression and also gender studies scholar. So what we were interested in was how gender fairness can be integrated in the design of social assistive robots, and what are implications for human-robot interaction designs when a reflection is made about the norms at play in this specific scenario. So what we have found from the interviews is that the experts we have interviewed think that a robot with feminine traits might be preferred And this is probably due to the fact that, and the importance of self-other similarity for the purpose of robot acceptance. So in this case, it's similarity in terms of gender. On the other hand, there was also some concern that this may carry the risk to perpetuate gender stereotypes. So on one hand, feminine appearance might be important for the issue of or the importance of self-other similarity, but also some risks also to take into account. So gender stereotypes, depending on the type of role that the robot might play. So if we think, for example, about the robot playing the role of a nurse interviewing pregnant women during a pregnancy or post-pregnancy screening if the child is born. So we know that most nurses are female. So if we think about a robot whose appearance is feminine, we might contribute to perpetuate gender stereotypes that nurses and also robotic nurses are female. So there are some interesting questions here about how to find a good balance in these specific scenarios, which I believe have a lot of connections with our discussions on personalization. But beyond appearance, there were also some interesting reflections on the need for such robot to be able to personalize to users and be adaptive. So personalization and adaptation skills, and primarily empathy came up as a key ability, but also lower level empathy, including mirroring of users' behavior. So to conclude now, so we asked these questions at the beginning of the presentation. So how can we build human-centric, personalized human-robot interactions? And we have seen that adaptive personalization is very much scenario dependent. So it may vary depending on the type of task and whether it is a scenario which involves both task and social components. We also saw that there may be some contextual factors to be taken into account, such as the perception of the robot over time, which again is important if we want to build robots that engage users over long periods. And what my work so far has suggested is that personalization should be considered as a multifaceted concept. There are very many different ways to personalize, not necessarily personalized to individual users, but perhaps to also category of users. And all of this work is, again, very much context and scenario dependent. But this context dependency and also differences across scenarios is also very important when we think about what we discussed at the beginning, the need to build human-centric robots, because clearly in this case, human-centric personalization is key for fair and trustworthy human-robot interactions. And it's the end of my presentation, but very shortly, this is clearly the work of many collaborations over the years with colleagues that I mentioned here. So thank you for listening, and I'm happy to take questions now.
Okay, so we have maybe time for just one question. If anyone has a burning question that they're dying to hear, maybe just drop it in the chat. And I'll give that a few seconds. Otherwise, I do have one that I was interested in hearing about. I think we'll just go with that. Great talk, Ginevra. Thanks so much for sharing that work. Looking at the first video you played, I was kind of struck because I've seen a lot of more advanced facial recognition and sort of like action detection frameworks come out over the past few years. So I was wondering if you could speak a little to how robots' perceptual capabilities have improved over time and how new kinds of perceptual abilities maybe have changed the way that you think about personalization in multimodal interactions, or changed the way that you are able to personalize in multimodal interaction.
Well, yes, you're totally right. So this early work goes back to more than 10 years ago. So there has been indeed a lot of improvements when it comes to detection and tracking of facial expressions and nonverbal behavior. And it's not my main area of interest of work at the moment, but clearly it is to be expected that systems robustness and accuracy play a key role, but not only in the context of personalization, but again, if we go back to the questions, the need to build a trustworthy AI and robotics, human-centered AI and robotics, clearly we need systems that are robust. And here specifically, there are also the pressing questions, which I think is still clearly under address of what is the effect of failed interactions or kind of wrong interactions, or inappropriate behaviors that are generated by a robot on the acceptance. I think the two questions, the ones that you mentioned, and this one go hand in hand, and I hope we'll see more and more research on this in the future.
Cool, thanks for sharing that. All right, well, I think we'd better get on to the next session, which is paper session number 1. And I am chairing that session conveniently. So our first paper up is Personalized Behavior Models, a survey focusing on autism therapy applications. And I think we'll have Michal Stolarz presenting that.
Yes. Hello, and let me share my screen. Okay. So, hello everyone. I'm Michal Stolarz, and with Alex Mitrevski, Mohammad, Wasil, and Paul Plöger, we would like to present our work, which is a survey on personalized behavior models and about autism therapy applications. And this work is conducted in the context of MIGRAVE, a project founded by the German Ministry of Education and Research. Our motivation is currently that a lot of children are diagnosed with autism spectrum disorder and they need a specialized therapy. However, those children find robots easier to communicate with than humans, and thus robots are included in such a therapies. However, human has to remotely control the robot most of the time due to environmental complexity. Thus, it is desired to increase the autonomy of the robot. So our goal is to provide a survey that aid and design of solutions for increasing autonomy of the robots used in ASD therapy. And it can be done by applying behavior models that allow the robot to choose a proper action as in response to the certain child behavior, user behavior. And this behavior model should be also personalized, namely it should adapt to the individual user over time. So we identified 4 personalized behavior models. The first one is social behavior personalization, which is about providing feedback to the user such that it stays engaged or motivated during the game or during the therapy. Another is game difficulty personalization. The third one is affective personalization, which is mainly about the robot maintaining its own affective state, which then affects its actions. The last one, personalization, is this based on users' preferences, such as speech volume of the robot or distance between the robot and the user, preferred by the user, called proxemics. We found out that 2 of those approaches are not used in the autism therapy because, for example, affective personalization might cause the autistic children to be overwhelmed by the changing emotion, affection of the robot. And when it comes to personalization based on users' preferences, up to our knowledge, it's not present in the literature, but we see here an opportunity as the robot can adapt itself to the sensory difficulties of the child. And now I would like to move to 2 approaches present in the literature when it comes to autism therapy. namely social behavior personalization, with which I would like to start, and then game difficulty personalization. So coming to social behavior personalization, the promising work was introduced by Emmanuel Senft in 4, where the neural network was introduced. The system was able to provide an engaging feedback to the user, and in order to not perform an undesired actions, it required also the supervisor that could correct the actions. Here, the neural network had to be fully retrained each time the new data was obtained. Thus, it was not suitable for real-time performance. This deficit was faced with Q-learning in 5 and nearest neighbors in 6. In 6, the system also needed a supervisor, but it could perform a huge variety of actions, and it was tested with children. When it comes to game difficulty personalization, we identified work number 7, where 2 Q-learning algorithms were used. One for adapting the challenge of the game, and second one for providing help for the user to solve the game in which he/she was taking part. Another approach in 8 combined both social behavior personalization and game difficulty personalization into one Q-learning algorithm. In our work, we also defined challenges in applying those behavior models in autism therapy. First of all, it is required to have a big state and action space for personalizing the game difficulty and also social behavior of the robot. It can be addressed with work number 6, which was the use of nearest neighbors, as I already introduced. Another challenge is fast convergence to a policy that will be able to successfully adapt the user, and without the need for significant number of interactions between the user and robot. It can be addressed with work number 8, where the policy can be pre-trained on the user model. Another challenge is that not a lot of works introduced experiments with the real people. And lastly, the systems that rely on the supervisor correcting its actions has to be resistant to also the mistakes of this person, which can be addressed by combining several signals from the environment, like in work 9 and 10. In the future work, we would like to deploy the QT robot that would work as a tutor in a tablet-based therapeutic games. It will adapt the game difficulty as well as social behavior. To summarize, I would like to say that we provided an overview of different personalization techniques in HRI field and child-robot interaction field. We found out what personalization techniques are not used in autism and which one can be used. And we formulated the challenges in applying those behavior models in the context of autism therapy. Thank you very much for your attention. This is the end of my presentation, and feel free to ask any questions.
Okay, thanks for that great presentation. If you have any questions, please drop those in the chat or okay, so I do have one question here, and this is kind of about the branching of social behavior personalization and game difficulty personalization. And I agree that these two techniques are typically distinct in a lot of projects. I'm wondering if you think that there's some, let's say, like benefit maybe to treating those two different kinds of personalization separately, as opposed to having some sort of joint model that kind of, optimizes for those two different objectives at the same time. Do you see sort of advantages to one formulation versus another?
So according to our work, we found out that game difficulty personalization and social behavior personalization might be, but don't have to, rely on different features. Like game difficulty personalization might rely on the game performance of the user, and social behavior adaptation might rely on the user's engagement, for example, and motivation for the game. But it doesn't have to be really separated. It might work together, as in one of the works that was provided here. And yeah, I think our approach will be in this direction, to combine those two together in one learning model as well.
Cool. That sounds very interesting. I look forward to hearing more about that work. All right, I think let's move on to our second paper of the session, and that is Adaptive Robot-Assisted Autism Intervention for Children with ASD. And that's by Anara Sandygulova, Aida Amirova, and Zhansaule Telisheva, who I think are going to present for us.
Do you see my screen? Yes. Okay, cool. Hello, everyone. This is our workshop paper titled Adaptive Robot-Assisted Autism Intervention for Children with ASD. This work is done in collaboration with University Medical Center. Here, let me introduce co-authors: Anara Sandygulova, Aida Amirova, Zhansaule Telisheva, Aida Zhanatkyzy, and Nazerke Rakhymbayeva. Let me tell you a couple of facts about ASD. In fact, autism or autism spectrum disorder refers to a broad range of conditions characterized by challenges with social skills, repetitive behaviors, speech, and nonverbal communication. We know that there is not one autism, but many subtypes, most influenced by a combination of genetic and environmental factors. So that the short-term nature of autism therapy with a social robot possesses another challenge to the HRI community to generalize process made about robot-assisted autism therapy. In our study, we refer to the concept of adaptability. The therapist adapted each session according to the child's behavior and reaction to robot activities in order to increase children's involvement and consequently to benefit from the therapy. Therefore, all sessions were divided into two conditions, adaptive and non-adaptive sessions, to understand how the adaptability of the intervention improves behavioral outcomes such as engagement, balance, and other social skills. This COMCORE project, project is conducted in collaboration and on the premises of the Republican Children's Rehabilitation Center in Kazakhstan. This medical center provides a full-fledged integrated model of rehabilitation using innovative technologies. Children with their parents are hospitalized for 21 days to undergo a 3-week therapy that includes traditional methods of autism therapy. Our study was approved by the ethics committees of Nazarbayev University and the Republic Children's Rehabilitation Center. It was carried out between 2018 and 2019 and included 4 cohorts of children to adopt robot-assisted autism therapy within the traditional autism therapy framework established in the rehabilitation center. To evaluate multi-session robot-assisted autism therapy with children with ASD, we carried out a long-term and real-world study, and these 2 hypotheses were formulated to test which of the adaptive sessions will lead to increased engagement and balance scores over time. Here's the information about our participants. There was a total of 34 children, 2 girls and 32 boys, ages 3 to 12 years old. Most children were nonverbal with an average ADOS-2 score 6.08. This table presents the participants' characteristics and information about the attendance sessions.
Here you can see the breakdown of children into subgroups. 10 children there were 10 children with high functional autism form and 24 children with low functional autism form. 12 children had the co-occurring ADHD diagnosis, while 22 children had ASD only. 11 children had speech abilities and were labeled as verbal, while 23 children were characterized as nonverbal. Also, we divided children by their age into 3 groups.
Okay. Hello, everyone. So, yeah, let me continue. So regarding our methodology, each child attended a series of 15-minute sessions with our robot. So the average amount of sessions that children attended were 7 sessions out of 10. Regarding the setup, all sessions took place in a small room without furniture. A child sat on the floor to maintain eye contact with the robot and see its behaviors clearly. Also, we placed 2 recording cameras in the room. So the first camera recorded child behaviors, while the second camera recorded the whole room. We developed various activities to be performed by the robot. Overall, we designed a total of 26 activities in both Kazakh and Russian languages. So these activities received inspiration from applied behavior analysis principles and generally used various techniques enabling pro-social and emotional behaviors. Robot behaviors target children's emotional well-being, joint attention, imitation, tactile contact, concentration, and imagination skills. And here we developed 11 assessment metrics by adapting those used in previous studies, as shown in the table. So 2 researchers coded a total of 46 hours of video with an agreement score reaching 82%. So on the next slide, you can see our results. So we have conducted a series of 1-way, 2-way, and mixed ANOVA tests. And we decided to analyze if children's individual differences in combination with adaptive factor have an effect on these 11 measures. So we have found several significant differences. Firstly, we have found a significant difference in engagement time between adaptive and non-adaptive sessions for children with high functioning autism. In contrast, children with low functioning autism didn't have such differences. Next, regarding the children's verbality factors, here you can see verbal children were significantly less aggressive in adaptive sessions compared to non-adaptive. However, non-verbal children in non-adaptive sessions were less aggressive. Also, non-verbal children were more curious during adaptive sessions compared to verbal children. But in non-adaptive sessions, the pattern was a bit different. So verbal children were more curious, while non-verbal children were not. So lastly, regarding the children's age groups, our results showed a significant difference in smiling of these children, aged 5 to 6 years old. They smiled significantly more in non-adaptive sessions. Also, there was a significant difference in engagement time between adaptive and non-adaptive sessions for children aged 3 to 4 years old. So finally, on the next slide, we are going to present key takeaways emerging from our study. Firstly, despite the severity of ASD symptoms, children with LFA and HFA spent more time interacting with the robot in adaptive sessions. Secondly, the adaptability of sessions showed different results in aggression and curiosity levels of verbal and non-verbal children. While verbal children were less aggressive and less curious in adaptive sessions, non-verbal children were more curious but showed more aggressive behaviors in those sessions. Also, lastly, even though young kids were more engaged in adaptive sessions, children at preschool age showed more affectionate behaviors in non-adaptive sessions. So on the next slide, you can see the list of references we used for this presentation. Thank you for your attention. Looking forward to hearing your questions and feedback.
All right, thank you for that great talk. Let's see, do we have a few questions in the chat? I don't think we do. Anyone in the audience just want to shout one out? I know I missed one from last time. No? All right, well, we are running a little bit behind, so unfortunately, I think maybe we'd better just move on to the next part of our program, which is the breakout session. So please give a quick round of applause for our presenters and our keynote speaker, and then we will move on to the first breakout session.
Hey everyone, so I'm going to be sharing the breakout session. So what we're going to do is I'm just going to take a minute to explain what we're going to do, and then I'll break you out into breakout rooms, and we can go from there. So for our first breakout session, we're going to put you into rooms and just have you briefly introduce yourself and your research. I think it would make the most sense to basically just have everyone go into turns, just talk for about 2 minutes so that everyone has a chance to kind of walk through and let you know what you're researching and kind of what your research interests are. And then what we'll do is after that, we'll come back, and later when we do our second breakout session, I'll put you into the same rooms such that you guys can discuss another question that we pose, and you'll have the same group of people that you just met with. So let me go ahead and do that right now. Let me know if anyone has any questions. Feel free to drop them in the chat, but you should be getting to your rooms in just a second. All right, I think we should be ready to get started. So I'm going to go ahead and introduce our next speaker, Vincenzo Lomonaco. Vincenzo is an assistant professor at the University of Pisa, Italy, and he's the co-founding president of Continual AI, a nonprofit research organization and the largest open community on continual learning for AI. He also serves as a co-founder and board member of AI for People, director of the Continual AI Lab, and a proud member of the European Lab for Learning and Intelligent Systems. Before this, he was a postdoc at the University of Bologna, where he also obtained his PhD. He's also been a visiting research scientist at a number of places, including AI Labs, Numenta, ENSTA Paris Tech, and Purdue University. And his main research interest is in continual learning and all of its various facets. And he studies continual learning under 4 main lights: deep learning, distributed learning, and practical applications, all within an AI sustainability developmental framework. And today his talk is titled X Model Continual Learning, a New Paradigm for Distributed Robotics Intelligence. And we are very excited to have him with us today. So with that, I'll hand it over to you, Vincenzo.
Thank you so much, Aditi. I hope you can hear me well.
Yes.
We'll see the screen and the laser pointer. Okay,
yes.
That's cool. Thank you so much, and thank you to all the organizers actually for the invitation. I'm very glad to be here for this, I think, the 3rd or the 4th edition of this workshop on lifelong learning and personalization in long-term human-robot interaction. So thank you so much. Thank you to all of you that are here for this talk. I will skip my introduction since you give a very, let's say, broad introduction myself. Thank you so much again. And I will just skip to the main discussion topic of today's talk. So how we can bring together a bit closer, I guess, continual learning and distributed learning, and how the robotics field can benefit from it. So I'm just gonna give a, let's say, broad talk about this within the scope of this new paradigm, what we call new paradigm, X-model continual learning. So the talk is going to be split in 3 main parts. The first part, just common ground of the shared and common view on continual learning. So what it is, continuous learning is all about today. Oops. Then the second, say, core part of this talk is going to be about introduction of this new continual learning paradigm, X-model continual learning, that is learning from trained models. And the third part, we focus very briefly on, let's say, opportunities and challenges for distributed continual learning more in general. So even going beyond X-model continual learning. So let's start. I guess many of you know already about continual learning, but there may be some of you from the robotics world that may be, let's say, less exposed, let's say, to this new line, let's say, of research in machine learning. Okay, so continual learning is mostly about learning from a stream of data, non-stationary data. So we are kind of moving away from this rigid separation between training offline and deploying a model with frozen learning capability, and instead moving towards like a smoother way of learning where we constantly update our biased understanding about the external world, always improving and generalizing over time. This you would say way of thinking about learning is particularly interesting for robotics and embedded systems, IoT systems, because may allow us to dilute somehow learning over time and make it reasonable in terms of computation and memory of threads, and making essentially scalable in terms of intelligence by essentially allowing ourselves to just generalize and learn over time, and let's say adding new knowledge only as we need it. So without this assumption, this idea of having a representative test set or a training set, well, and fix, let's say, objectives and goals, and instead trying to have a single parametric model most of the times that learns how to acquire new skill and builds on top of what they've previously learned. And practically speaking, this often translates in, let's say, mapping function, for example, here, f of theta, that is trained to map examples belonging maybe to two different distributions, x1 and y1 distributions. As essentially we move on and we encounter new examples belonging even to different distributions, so new couple x2 and y2, what we would like to do is to generalize this previous parametric mapping function so that we can handle both couple of distributions, but without accessing anymore the data related to the previous couples, x1 and y1. And this would allow us to be sustainable in a sense, constant in terms of resources that we deploy to our system, but at the same time being able to adjust, to adapt our agent brain, right, our robotic brain with new data and with the ever-changing nature of the environment in which we are supposed to operate. And let's say over the last few years, continual learning has been focusing on let's say different scenarios in which I think the shared assumption is essentially that we are allowed to process a set of data belonging to a particular computational step. So in this case, I call these steps like experiences, so a number of experiences we encounter over time. Within these experiences, we may encounter different examples. For example, in this case, I just list like x1 to xn training examples with the corresponding labels, as well as having access to a number of additional, say, supervised learning signals, like labels describing the particular task we are solving, the particular distribution this is generating somehow these examples. And these examples may be related to, I don't know, images for classification tasks, maybe sequences, or anything we may think in a general machine learning task. Following, let's say, this main idea of continual learning, I think we can see it as the next, let's say, imminent step towards systems that are both more functional as well as more biologically grounded. So here in this plot, in this picture, please take it with a grain of salt. What I try to do is to show that as we're trying to develop more and more effective computational models or learning algorithms over time, we are somehow taking more and more inspirations also from biological systems with different degrees of success. And so just focusing, for example, on the red dots here, highlighting just the, let's say, neural network-based approaches, we started from solutions just leveraging the homogeneous feed-forward neural networks for learning arbitrary tasks, and then trying to add a bit of let's say, architectural insights from the visual cortex and improving a little our ability to solve more complex tasks, moving towards like deeper convolutional neural networks, then adding, let's say, the notion of time with convolutional LSTMs, a mixture of recurrent neural networks and convolutional neural networks, and even trying to lower the amount of supervision, taking inspiration also for biological evidence with deep reinforcement learning strategies. And so I think that continual learning may be indeed seen as the next step towards more grounded and more scalable, efficient, and effective learning algorithms that are indeed inspired by nature. However, so within this idea of developing continual learning as a biologically inspired and grounded approach, we fall into this idea of agent-centric learning and view of the world. So continual learning algorithm is often thought to be trained as a single agent that is exposed to this sequence of experiences, this, let's say, stream of raw data that an agent is supposed to encounter during his immersion in a particular environment to solve a particular task. So for example, a robotic hand that is somehow exposed to different objects that it needs to learn how to grasp, right? And so the main assumption within this line of thinking and the idea of continual learning algorithm is that we should try to aim for a list of desiderata, like learning in an effective way, but also being able to be mostly replay free. So without storing so much examples about the past and rehearsing from them to avoid forgetting. The idea to be constrained, limited, somehow bounded in terms of computational and memory resources that we deploy to our system. So that, for example, we may think of having these continual learning algorithms running directly on the edge of these robots, as well as trying to leverage as little as possible additional supervised learning system, learning signals like these concept of task labels or labels describing where a shift in the data is actually happening. So we would like to have our robotic arm, for example, to learn by itself when something has changed, if the rules of the world that in which it is operating are changing, and adapting swiftly without any human intervention. And finally, we would like to have systems that are very quick in adapting to new, let's say, circumstances and situations without waiting so much evidence to come available, and just updating maybe on the fly with a new interaction with a few examples. And so these may improve also the reactivity of our system and make it really autonomous and robust to sudden, for example, change in the world. So these are the main desiderata that are often considered within continual learning and within this agent-centric view of the same. But I think that we are now somehow encountering a fork in the continual learning road. So I think the continual learning community is now mature enough to consider different alternatives. So it is true that biological inspiration, biological learning systems constitute today the best representative example of systems that can learn continually in an effective and efficient way. So we can take a lot of inspiration from this. I think it is a path worth pursuing for continual learning. But at the same time, we should try to not limit ourselves within this agent-centric view of the world and leveraging instead what we learn, especially within computer science and machine learning, with systems that can be distributed and can exchange information among each other to improve the overall quality of the service provided. So I think that for continual learning and robotics, this may be a different path because it is different to make it converge with the other view of a biological inspired and grounded way of learning, but nevertheless, very interesting to investigate for the future research in this area. So, for example, within the robotics world, we may think of a fleet of independent robots that learn how to grasp different objects over time. So, for example, robots related to a single company, robots instead that are distributed across different companies and maybe also coming from different stakeholders. So in a completely decentralized, let's say, world, they try to learn how to grasp different objects depending on the task they are aimed to solve. But in this ideal world, I guess, will be very, very nice to reuse as much of this expert knowledge that is learned these different maybe locations from these different agents, being able to maybe improve the efficiency of learning instead of just learning by examples every time, and being somehow able to be still independent from the rest of the agents. So this fleet is indeed a collection of agents, maybe homogeneous in terms of hardware, for example, but maybe interesting to have them completely independent among each other. So they should be able maybe to be fine-tuned to solve specific tasks and be completely free of any protocols, as a standardized protocol among each other. That would be quite interesting. And also, I think it would be very nice to, within this context, to tune with a finer grain the privacy that we want these arms to be subject to. So privacy rules different for every device and task. And so I think that towards this vision, the current continual learning solutions provide only a partial answer. And we would like to instead leverage more maybe these models that are trained on this different location with different data, and reuse as much this knowledge from expert models. For example, starting from local personalized models or large pre-trained models as well. And this may impact very much also on the sample, what I call sample efficiency. So that we don't need to start every time from scratch. We don't need to learn from examples, from experience directly, but we may, that is subject, I wanted to say, on to noise and redundancy, as we know that some particular data sources may not be that efficient overall. So in the end, we would like to share a bit of knowledge among these different agents, right? And learn independently, as I mentioned before, and efficiently at the same time. Finally, for privacy, current continual learning solutions alleviate a bit the problem of privacy, because we may get rid of data as soon as we have learned what we needed from that. But at the same time, we still have to somehow have access to these raw data that may be user sensitive. So in order to fulfill a bit these issues and missed opportunities, I mean, we proposed a new paradigm that we call X-modal continual learning, because starting from Latin would mean from models. So continual learning from pre-trained models instead of raw data. And so essentially, this paradigm is quite let's say simple to straightforward to explain, starting from the general let's say scenario that we were used to have in a continual learning setting. So in a continual learning setting, as we were saying before, we would like to have a parametric mapping function f of theta that is constantly updated based on new evidence, based on new examples that we encounter for each new experience. So for example, in this case, new images or particular objects we encounter over time. Well, for an X-modal continual learning setting, what we are saying is essentially that we don't have any more access to the original data at any point in time. We only have access to pre-trained models, for example, encoding that particular skill or recognizing that particular object. I mean, in our case, for the robotic arm, it would be to learn a model that is able to grasp that particular object. So what we'd like to do is to learn directly from these models that we encounter over time, in the same way as we would do for a continual learning algorithm, without any access to the original data on which these experts models have been trained on, okay? And we will still end up with let's say a single parametric function f of theta that should be able, as the original model at the end of the training, to distinguish maybe all these objects, to grasp all these objects. And, the only, let's say, change that we made here is the access to the original data that is substituted essentially with this availability of trained models. And this is quite interesting because help us, let's say, to solve all the issues and let's say missed opportunities that I described before. So we don't have any more access to the original data, so we can be like private by design. So we never share private data, across the network, and we share only, let's say, expert models. We can be, let's say, quite efficient in terms of learning, because we can just integrate new compressed knowledge. So instead of learning from noisy and redundant raw data and learn directly from experience, we just learn from a compressed form of knowledge that is an expert pre-trained model. And so this is quite, I think, in line with what we do as humans as well, right? So we do not, if we want to learn a task, we don't start just by learning by trial and errors, but what we do is just look maybe on the internet and find a nice tutorial, nice book that is explaining exactly what we want to solve, right? How to solve it. And so this is exactly what we should aim for models as well. So starting from compressed form of knowledge that somewhere else in the world has been already acquired. And so what we do is to still allow ourselves to maintain, let's say, a fixed size external memory in which we can maybe generate some surrogate examples or maintain some out of distribution examples that we can later use, and we'll see how in a baseline that we implemented for this. But that another important assumption here would be to not maintain all the experts model into the memory. So this is in line with the assumption in Continual learning that we should try to be constant in terms of computation and memory resources where we give to our system. So we cannot store all these different F1, F2S down below here and expert models. We should try to find a way that is sustainable long-term to learn a next model overall, let's say, continual learning model. So how we can do this? So our, let's say, basic baseline that we introduced in this paper, X model, continual learning from a stream of pre-trained models. You can more details on this paper, this preprint and archive. What we do is essentially use a basic double distillation strategy that goes as follows. So what we do is to start from at every time step, we have access to a new expert, right? This Fi of S. So what we do is to have, say, an inversion, essentially, algorithm that is able to extract with a particular technique surrogate examples, training examples from these trained models. It can be also like an arbitrary model, not necessarily a generative model, right? And when we have created somehow a representative set of, extrapolated a representative set of examples from this expert model, we should try to do the same, with the continual learning compressed, let's say, model we have up to the time available, or we can just have a set of examples that we have generated from previous time steps. Well, in any case, we can have a double distillation loss that is able to essentially create a new model that is enumerating both knowledge, so from the new expert and the continual learning models that we've been training over time. And so we can create essentially a new model that is able to merge these due to knowledge sources through distillation. I hope you have some basic knowledge about knowledge distillation, but essentially here we are trying to add, to create a loss function, to replicate the output of these two different models based on some input examples that are generated here over time. So another important aspect here is that we should try to remain as much as possible agnostic, not only to the model's topology, so the topology of the model we're trying to learn from, but also in terms of the continual learning scenario we are taking. So in this paper, we are trying to be as general as possible, and so we propose a number of experiments that are tested on, say, common continual learning scenarios, like class incremental settings and domain incremental settings, multitask settings, and so on and so forth. So here I just report a couple of results for the few baselines that we proposed that you can see here at the bottom. So model inversion, X-model distillation, data impression, X-model distillation, auxiliary data, X-model distillation. So in this case, the only difference among those is how essentially the data for the distillation are generated. So in the first case, we used a model inversion algorithm. The second, data impression algorithm, so just two ways of generating examples from an arbitrary trained model. And the third one being data that are not actually generated from the expert, but are auxiliary data that we know are relatable to the distribution on which that particular expert has been trained on, so that we can use this for distillation. And so, as you can see here, well, we don't have time to go through all the details of the results. You can check the official paper for that, but the results are quite, let's say, low, showing that this kind of setting is quite challenging for current continual learning strategies, and at least as we proposed it so far, leaving a huge space for explorations and improvements. But at the same time, we can see that I mean, these strategies are quite competitive with respect to the basic, let's say, baseline of parametric average. It is the standard for federated learning. So here at the top, I just lead to a couple more baselines, just to understand a bit the context in which we operate, that are not X-model, let's say, strategy, continual learning strategies per se, but just are interesting baselines which we can compare our results. For example, just to show one of those, an ensemble of all the experts that we said we cannot maintain to memory, but for the sake of clarity, and here we also show these results, where we essentially tried just to have an average, let's say, of the predictions, and try to make prediction based on this huge ensemble of models. So I just wanted to conclude this talk, trying to understand how X-model continual learning is positioned with respect to a more general distributed continual learning idea, trying to highlight what are the current, let's say, challenges, and especially looking about the future opportunities. So what we have seen briefly through these results, and if you look at the paper more carefully, is that the idea of a dual model distillation strategy is quite complex. Well, in general, it's complex to merge two models, two pre-trained models without the original data. So this is an open challenge, is at the core challenge for distributed continual learning strategies. Then another important, let's say, issue to apply is this complexity related to the idea of generating training examples, starting from a trained model, maybe even without a generative model, and being able to do so in an efficient way. So this is quite tough at the moment, given the current methodology that we have today. But it is interesting to know that some selective pruning plus ensembling methods may provide interesting solutions, especially practically, to solve this problem, especially if we are processing a stream of experiences that is limited in terms of numbers. And finally, what I want to stress here is also the fact that we tackle the problem here. We define the X-model continual learning problem in a very general sense. So that's also one of the reasons why this is so complex. And I think that we may allow ourselves for some simplifications of the problem's constraints. For example, a shared training protocol for all the experts, like, for example, allowing ourselves to maintain a generator for each of those experts, or other possible tidying constraints, like specifying the specific settings in which we operate, and other constraints that may be realistic depending on the specific application context. And this may significantly reduce the program complexity, of course. And so in terms of opportunities, I also wanted to highlight the limits of other, let's say, more common distributed learning, let's say, paradigm, like federated learning. So federated learning may be used as well for like similar ideas. Maybe you already have some knowledge about applying federated learning to specific robotics problems. But I think that federated learning is limited in a number of ways. And for example, it requires like a frequency synchronization about among all the different entities participating to this federated learning. It requires like a stable internet connection, and also a somehow shared single stakeholder training protocol. This also implies a form of homogeneity in terms of modular architecture, topology of the different predictive functions at any location for each different device. And we know also that federated learning is, by design, as it is proposed, not able to handle non-stationarity. So we need something else in case we are operating not only in a distributed but also ever-changing context. It is quite normal, I guess, when we're dealing with let's say, a diversified and different set of devices scattered across the world. So another interesting point here is that federated learning can be seen as a constrained version of what we discussed to be the X-model continual learning paradigm. So if you think a bit more carefully about this, X-model may be somehow constrained so that it becomes a form of federated learning. So this is quite interesting because it would suggest that essentially this idea of X-model continual learning may be seen as a more general way of doing distributed continual learning and distributed learning in general. And finally, I wanted also to try to think of possible applications of X-model in the long term. I think this part may open the path to, let's say, marketplace of neural skills for AI systems and robotics, for example, where we may think of, let's say, shared knowledge pools, let's say, a pool of compressed knowledge that can be injected in our robotic systems just when we need it. So as soon as we need a particular skill, we may just integrate it on the fly based on this idea of marketplace of shared neural skills or pre-trained predictive models. And I think that X-model continual learning provides a new exciting path for distributed continual learning in general, and especially for robotics intelligence, let's say, distributed platforms that I think would highly benefit from this kind of distributed continual learning approaches. So with this, I concluded my talk, and I would like to thank actually all the people that are involved with this in this paper, especially Antonio Carta, who is the first author of the paper, Andrea Cossu, and Davide Baccio were also very much involved in the development of this project. And all the people actually that are components of this continual learning lab that we are pushing forward here at the University of Pisa. And I invite you to check out our official website, and why not to send us an email if you want to learn more about our activities, and to join us, visit us directly in Pisa. So thank you so much for your attention, and we are now open to your questions.
Well, thank you so much, Vincenzo, for that awesome talk. I'll just give everyone a few minutes to stick some questions in the chat if you have any, and in the meantime, we can go ahead and get started. Looks like, Hatice, you had a question, but it seems like you said he already answered your question. Did you have another question to follow up there? If not, no worries. Bahar, do you want to ask your question?
Yes, thank you very much for the fantastic talk, Vincenzo. It was really great to that you give an overview of all the continual learning approaches. I was wondering, let's say we have a robot out in the real world, for instance, doing household chores, but in a completely new environment than it's trained to. How can your model or another continual learning model can learn to generalize to unseen settings and personalize the user preferences in zero or few-shot learning settings so that we don't create damage to the household that might be unpleasant for the users?
So if I got your question, you're asking how we can specialize, fine tune a particular model without hindering somehow the previously learned knowledge,
and in a few shot settings, so that we don't do many trials and like, I don't know, like break dishes or something in a household setting.
Well, so there's a lot of literature, let's say, at the crossroads of continual learning and few shot learning. But I'm not an expert about this, but what I can say is that it seems to be quite commonplace nowadays to just fine tune, let's say, a new ad or let's say just the final classification layer to suit a particular task, and that in general is very let's say efficient and also requires a few, let's say, examples just for the sake of a particular task. So that's also somehow, I think, answering a bit to your question in a sense that it is reasonable to think at continual efficient, effective continual learning solutions that have somehow a static somehow feature extractor, and they may be fine-tuned and specialized very quickly to suit a particular task. And another important note on this, I have seen that there has been now a lot of interest in these foundations models, right? So these models are trained on a huge amount of unsupervised data, especially in NLP, but I think nowadays we're talking also more and more about unsupervised models trained on computer vision data as well. And I think that also poses an interesting question for us, let's say, continual learners, because it seems that these features are so robust that maybe we may also change our main idea of learning continually. Instead of finding a way to add new knowledge and over time, maybe moving towards this idea of just having fast adaptation, right? So instead of trying to not forget, why we instead focus on just efficiency of the adaptation. And so maybe that's also related a bit to your question, but I think it's a quite interesting also new trajectory that we may want to investigate.
Absolutely, thank you very much.
We do have another question in chat, kind of a follow-up from before. She said, perhaps you can tell us about any disadvantages or challenges of using distributed CL or continual learning.
Yeah, I think that, so as I mentioned a bit in the talk, adding a new dimension of complexity, let's say, to the problem, this idea of distributed other than continual, it's adding it imposes us to think deeply about the implications of this, but also it is quite difficult to do in general with the current methodologies that we have. So, for example, knowledge distillation is a powerful tool that we use, commonplace, I would say, in CL, but it is still difficult to use it, especially when you don't have the original data, the original training data. So that's something that I think it's challenging and is currently missing from the literature. And more in general, this idea of merging two pre-trained models, it's something that it's not easy to do. So even without the notion of continual learning, merging knowledge from models, it's an open question, I believe. And so nowadays, what I wanted to stress is that it seems to be more computationally, let's say, difficult to start from compressed knowledge than starting from raw data. So this is quite counterintuitive, I think, right? So you have knowledge that is already compressed, already learned, but if you want to merge this knowledge, it is more computationally intensive than starting from scratch from the raw data on which these two models maybe have been trained on. So that's quite counterintuitive, and it also shows how far I think we are in terms of understanding on how to put knowledge together in an effective way.
Awesome. I think we do have one, let's see. just had another question, because I was going to ask one, but it looks like we have one more coming. Let me just go ahead and ask that. So it says, you've addressed many shortcomings of existing CL, and of course it's more challenging to try to solve multiple problems at the same time. If you had to focus on improving one of these limitations at a time, which are we best positioned to push forward on right now toward making continual learning more practical and useful?
Okay, so continual learning in general, there are many interesting lines of research, I believe. So if we are talking about just more practical, right? So I think that the focus was on more practical and useful. Yeah. So in terms of application, I think that one trajectory that is very interesting to explore further is architectural strategies mostly. So these are there are a number of continual learning strategies that essentially can give you the possibility today to have kind of zero forgetting. So you remove completely the problem of forgetting with a low overhead in terms of memory sometimes. So I think that in terms of practical application, that's quite powerful, because in general, you don't have, for many application use cases, this need of fast adaptation, or the need to have a system that once deployed needs to process like thousands of different experiences. So if for example, time horizon is quite limited, you may think of different practical ways of achieving effective solutions that provide even zero forgetting, so without negative impact on your performance, and even quite efficient, still quite efficient in terms of memory and computation. So just to make mention, like there is a method is called piggybacking, essentially in continual learning, where you just have a fixed backbone and you add some masks on top of the weights or the activations, so that you can, based on the task you're solving, based on a specific distribution, you may somehow change the behavior and specialize the behavior of a particular model to suit that particular task. And so these methods are very, very efficient. So there are no actually downsides, apart the fact that they cannot be used for very long time horizon, and this idea of additional, say, supervised labels, they exploit many times. But in case you have like a short, let's say, sequence of well-defined tasks, I would go definitely and use these approaches. But even if you don't have task labels, there are many ways in which you can come up with interesting solutions that may make, let's say, these approaches useful as well. So I would say just they're not maybe the ultimate answer for a long-term continual learning vision, but they are definitely useful for practical application. Yeah, I would go mostly towards that.
Well, thanks so much, Vincenzo. Let's give a round of applause, and I think we can move on to our next paper session.
Thank you so much, Aditi. Thank you all for your questions and your attention. And please send me an email in case you want to learn more, or you want to send an additional couple of questions.
Yes,
Bye.
we'll do. Thank you. Looks like we have our next paper session coming up, so I will hand it over to Herman.
Yeah, thank you. So now we have our second paper session with three amazing contributions. I think we can start from the first one, which is Human Influence in the Lifelong Learning Reinforcement Learning Loop by, sorry for mispronouncing your names, Thierry Jacquin, Julian Perez, and Cécile Boulard. Are you guys around to present your paper? Awesome. There you go. So we can see your screen. Just want to make sure we can hear you. Are you talking right now?
No, sorry, I was mute. I will reshare. So just as an introduction to the talk, because I will play a video. I like the video because it's just restricted to 8 minutes, and then we can have time for questions. But just as an introduction, this talk it presents a very new line of research that is more oriented towards what Vincenzo, Lomonaco, designed as a fast adaptation of pre-trained or foundation models, if you want. Okay, that's the single introduction I would like to add. And then let me play the video. Tell me if you hear it correctly.
Everybody, thanks to the organization for the invitation. I am Thierry Jacquin, and I will introduce you to a new research project started within Naval Labs Europe. This work has been initiated together with Cécile Boulard and Julien Pérez, both recognized researchers in their respective fields, sequential decision models for Julien and human-machine interaction for Cécile. We place this work in the near future where robots will enter our everyday space. For task providers, the deployment phase at low cost is the challenge. Okay, the main hypotheses for lowering the cost are the following. The task model is pre-trained in a generic simulated environment. Okay, and then the task is adapted to the real environment, lifelong specifics. When we talk of lifelong specifics, is things that don't change very fast, okay? Typically geography, habits, laws. And what we want is to make this adaptation robust to model maintenance evolution through persistent adaptation schemes. And third, the lifelong adaptation to environment variability can be done in the same way, but then the pace of adaptation is faster. Seasons, erosion, trends, finance, regulation, who knows? But the underlying mechanism is always the same, influence. And when influence is considered in a loop by a human, and the human is able to see the effect of his influence in the way the agent is running his task, then we call this coaching. Okay, coaching is the fact of using influence in the real loop of action of the agent and witnessing how positive it is with respect to the human expectations regarding the way the task is run. And as human experts, we refer here to humans that are knowledgeable regarding the task to be done and the environment where the agent is evolving and associated risks. And there are no requirements of expertise in algorithm nor models of sequential decision making. Then we see that what we call influence, in fact, is a set here of small grounded preferences expressed by the user. In that particular case, it's where the blue arrow is represented. There is a preference of going to the right action. Okay, and the goal of this is to, in this particular case, this user would have recommended to go to the right in order to avoid collisions here. Okay, we'll see that in the next slide. But the idea is to bias the action that is computed from a logits at the output of this agent here. The logits propose a preference of action given the model. Okay, and then there is a selection in case of discrete action as it is in this model. There is a selection of the action, and then in fact, we change this selection. Prior to select this action, we multiply the logits of the policy with the preference associated with an influence. And an influence is computing a preference given an influence and a state. Okay, and so the scheme of influence is this number of grounded influences here, and the expert is able to design, in a sense, the set of influences he wants to provide to the environment, so that the behavior, the global of behavior for the task, is respecting his expectations. Okay. And what is interesting here is that this mechanism is fully external to the model. But if you want, you can then improve the model itself by merging this external influence with the policy itself, and you can learn from influence. And in that case, you only consider the influence scheme, and you design reward starting from this influence scheme, and you reinforce the reward with the fact that the chosen action is also recommended by the user in the sense. Okay. So if the action taken by the model is close to the action recommended by the coach, then the reward is stronger. Okay, and all the stakeholders can have expectation, and so this will enter, and the optimization of the model will respect all the stakeholders' expectations. In that case, it will optimize with respect to all the stakeholders' expectations. That's interesting. So in a particular case of the experiment, we did that only to as an initial step to see if it was interesting and if it was worth it to start a research line with that. And okay, so we see the original model of mapping as proposed by Chaplot. Okay, Devendra Chaplot, and then we just submit the model to an influence to try to avoid the collisions here, for example, or here, for example. Okay, and so when you're in this corridor, you go up to the right and you go down to the right, and there are less collisions than here, for example. And but this is at the price of the performance of the model. But here, because here, for example, the mapping is not done, here it's not done, here it's a bit imprecise, and so on. Okay, it's very imprecise compared to the original one. So, but you have a safe behavior of your robot, your mapper. So if you fine tune this and this, then you can go to something that is more performant but less risky. Still, you don't have so much collisions here and here compared to the original one, for example. Okay, we're only at the start of this adventure. It's a very initial work, but it was interesting for us to expose the direction of research we go in, and particularly because the modalities of coaching that we can provide on top of this influence mechanism are numerous, and probably potentially a lot of research lines going in various modalities can be initialized from that. Thank you thank you for listening, and it's now time for questions. I'll try to answer too. Thank you.
Yeah, thank you. Thank you very much for the interesting presentation. I think we have 1 minute for questions. If anybody has a question, please just write it down in the chat. Otherwise, could you please go back to the conclusion slide if you just have it handy? Otherwise, while we're waiting for anybody to submit a question. Right, I think we have questions at this point, so I'll go ahead. I have actually two original ones. First of all, in terms of when you say learning adaptations in a performant manner, so what do you mean by performance? So are we talking about like computation or speed? So what exactly is the performance axis that you have in mind?
Can you hear me? Yeah.
Yeah.
Yeah, it's the performance of the original task of the robot. Okay, so it's not the performance of learning, it's really the result in terms of the task. So in that particular case that we presented here, it's really the goal of the robot is really to map the space in which it navigates, and so at the end of the task, the performance is measured by the precision of the mapping it has of the environment he had to map. Okay, so here are the obstacles here in green, and here are the free spaces, and it's really the paper is really based on real environments that have been pictured, And of course, after that, it's simulated in AI habitat. But the important thing is that the mapping that is provided at the end of the task is close to the mapping that was given at the entry of the experiment. And when we consider performance, it's really this kind of performance. The task is modeled for achieving something special, and when you constrain it by inference, it's possible, and most of the time it will be the case, that the task is a bit degraded by the constraints that you provide through these kind of inferences here. Okay.
Awesome. Cool. Thank you. Yeah, for the sake of time, I think we have to move on to the next one, but thanks a lot. I do have another question, but I think we can take it offline.
Okay.
And thanks a lot for the presentation. So we can move to our to the second paper of this session, which is towards improving lifelong learning via personalized reciprocal teaching by Maria Shrum, Erin Hedlund-Botti, and Matthew Gamelay. Again, sorry for mispronouncing your names. Awesome.
All right. Can everyone see my screen?
Yes, we can.
All right, cool. So I'm Maria Shrum, and I'll be presenting on our work towards improving lifelong learning via personalized reciprocal teaching. For robots to operate in the real world, they must be capable of learning novel tasks from their end users. And they can do this via learning from demonstration or LFD techniques. And so prior work has shown that robots learn best via robot-centric LFD, in which the human provides corrective feedback to the robot learner. However, prior work has also shown that humans tend to be both suboptimal and heterogeneous when providing this corrective feedback, which can make it difficult for the robot to learn from humans. And so to improve upon the deficiencies in robot-centric LFD, in previous work, we introduced what we call mutual information-driven meta-learning from demonstration, or MIMELD. And MIMELD meta-learns a personalized embedding representing the way in which an individual is suboptimal. And then MIMELD utilizes this embedding to map suboptimal demonstrations to better demonstrations. And we demonstrate our architecture in a driving simulator domain. To learn the personalized embedding, we employ what we call calibration tasks. These calibration tasks consist of Wizard of Oz policy rollouts representative of the task space, and they have known optimal labels. For each calibration task, the agent rolls out its policy as shown on the right, and the demonstrator must provide corrective feedback. We then train our MindMeld architecture on the corrective demonstrations and the optimal labels to learn the personalized embedding and the mapping from suboptimal labels to better labels. And so in our prior work, we demonstrated in a human subject study that MindMeld achieves a lower average distance from the goal and a higher probability of reaching the goal compared to baseline LFD algorithms. We also showed that in the driving simulator domain, participants have a tendency to either over or undercorrect and provide delayed or anticipatory feedback. And so in this prior work, we've shown that MindMeld can effectively account for demonstrator suboptimality and heterogeneity. However, several problems arise when correcting for suboptimality under the hood. First of all, prior work has shown that humans tend to be poor teachers due to a lack of functional understanding of how the robot works. And this lack of functional understanding can lead to decreased trust and use of the robot. Additionally, producing high quality results from suboptimal demonstrations will only reinforce suboptimal behavior, and the demonstrator will likely never improve. And then lastly, we also hypothesize that humans will be better at generalizing to out of distribution tasks than a machine learning algorithm. And therefore, robots should work with their human demonstrators to help them become better teachers. And so to this end, we introduce what we call reciprocal MindMeld. Reciprocal MindMeld is based upon the idea of reciprocal teaching from the teaching and education literature, in which the student takes on the role of the teacher. And so our objective with reciprocal MindMeld is to improve demonstrations via robotic feedback, and then to improve upon a robot's ability to learn from a human demonstrator. Our reciprocal MindMeld framework is based upon the MindMeld architecture, in which we learn a personalized embedding via the calibration tasks that I discussed discussed earlier, and that describes the way in which a demonstrator is suboptimal. Our objective is to then shift this embedding closer to an embedding representing a hypothetical perfect demonstrator. And we accomplish this in 3 steps. We first must learn a semantically meaningful embedding space so that we can then communicate to the demonstrator the way in which they are suboptimal. Once we've done this, we can then provide informative and actionable robotic feedback based upon where the demonstrator falls within this embedding space. And then lastly, we want to be able to re-estimate the new location of the participants' embedding to determine if their demonstrations are now acceptably high quality or if we should continue to provide actionable robotic feedback. And so we investigate reciprocal mind melds performance in a driving simulator domain. And our objective is to provide actionable robotic feedback to reduce the amount that a demonstrator over or undercorrects and the amount that they are delayed or anticipatory in their feedback. And so to first test reciprocal mind meld, we first conduct a pilot study to determine if we can just shift a participant's embedding in the over undercorrecting dimension. And so in this study, participants first complete a set of calibration tasks from which we then can learn their personalized embedding. Based upon where their embedding falls within the embedding space, we then provide actionable robotic feedback. Participants then redo the calibration tasks so that we can re-estimate their embedding. And they do this for 4 rounds. And our overall objective in this pilot study is to determine if we can actually shift the participants' embedding within an acceptable range of the hypothetical perfect demonstrator. And so here we show the embedding space, which we trained on calibration participants collected in previous work. We train a support vector machine on these participants to separate overcorrectors from undercorrectors and those who are delayed from those who are anticipatory. And our objective is to provide robotic feedback to shift a participant's embedding closer to the hypothetical perfect demonstrator and in the direction of the arrow shown here. And in our pilot study, we are only interested in improving participants in the over-undercorrecting dimension. And so to do so, we measure the distance from a participant's embedding to the over-undercorrecting decision boundary. And then we provide actionable robotic feedback that is intended to shift their embedding into the top quartile of participants. In our study, we have 3 conditions. The first is a cooperative agent condition in which the agent provides feedback intended to actually improve the demonstrator's teaching abilities. In the adversarial condition, the agent provides feedback that is intended to make the demonstrator a worse teacher. And then in the none condition, no feedback is provided. In our study, we recruit 27 participants, and we show that in the cooperative condition, the participants' embedding does move significantly closer to the perfect embedding along the over-undercorrecting dimension. And we show that participants move significantly farther away from the perfect demonstrator in the adversarial condition. And that in the none condition, we don't really see any change in their embedding. Additionally, we find that participants rate the cooperative agent to be higher in terms of team fluency and trust. And so in future work, we plan to conduct a full pilot study investigating feedback in both the overcorrecting and undercorrecting dimension, as well as if we can improve upon participants' tendency to provide anticipatory and delayed feedback. We then propose to train an LSTM architecture to predict the participants' embedding on the fly so that the demonstrators don't have to repeatedly do the calibration task to re-estimate their embedding. And then lastly, we want to conduct a final study in which we investigate an agent's ability to actually learn from a demonstrator after that demonstrator has received actionable robotic feedback intended to improve their demonstrations. And so we'd like to thank our sponsors, and I'd like to thank my co-authors, and I'd be happy to take any questions.
Thank you. Thanks. Really interesting work. Yeah, so please, if you have any questions, write it down in the chat right now. I think we have time for one question. Just wait a few seconds here. But I'll start right away. I think, again, I do have a lot of questions. It's really interesting work. So in terms of, have you seen how maybe different ways of providing feedback to actually influence, the human in the loop to actually do better or worse? So
the robotic feedback. Yeah. So that's something we are investigating. So right now we're in the middle of conducting our pilot study, looking at if we can improve participants in the 2 dimensions. So if we can improve their tendency to over and undercorrect, and also improve how much they're either anticipatory or delayed. And so we're looking at if we should provide robotic feedback in both dimensions simultaneously, or if that's just like information overload, and if it's better to first just try and fix how, you know, they're doing in one dimension, and then fix how they're doing in the other dimension. But we are finding that it's actually not really information overload, that it's actually better to just tell participants how they're suboptimal in both dimensions. So does that answer your question?
Yeah, sounds great. And we have one more question from somebody in the chat, so I just want to make sure we have the time. So the question is, how did you quantify participants' trust?
So we just utilized a survey from prior work that we measured after the end of every round of calibration tasks. And then we just took the difference in their trust from the beginning of the study and the end of the study and looked at improvement in trust over the course of the study.
Awesome, thank you. So thanks a lot, Mariah, for the presentation. Unfortunately, we have to move to the next paper. We didn't have a lot of time. Again, thanks again. So we have the last paper from our session, which is a motivational robotic coach for repetitive individual training by Martin Ross, Frank Bros, and Lynn Bailey. Sorry.
Thanks. Can you see my screen all right?
We see your screen, not in presentation mode. Now we see it the right way.
Perfect.
Awesome. Thank you.
Nice. Hi, everyone. My name is Martin Ross. Today I'm going to be presenting our work on a motivational robotic coach for repetitive individual training, conducted alongside my PhD supervisors, Frank Bros and Professor Lynn Bailey. So as the title suggests, we're looking to create a motivational robotic coach, which can be used in 2 different use cases, one in the sports domain, and specifically we're looking at squash, and then one in the rehabilitation domain, so specifically we're looking at rehabilitation after a stroke. So why do we want to do this? Why are we looking at both of these kind of domains and use cases at the same time? Well, adhering to repetitive rehabilitation can significantly improve a stroke survivor's recovery in the long term. However, when this rehabilitation is conducted in the home without the supervision of a physiotherapist or a nurse or a doctor in hospital, adherence tends to decrease due to, among other reasons, a lack of motivation to do the exercise on your own. Similarly, in sports, so squash just being one example, repetitive individual solo exercises and drills are used a lot by high-performance athletes, but not so much by players at lower levels, indicating again a lack of motivation to do these exercises when the coach isn't present, so in an unsupervised setting. So can we use robots to help motivate individuals in these 2 different scenarios? Well, the research would suggest yes, we can. There's been examples of robotic coaches being used with children with cerebral palsy, with stroke rehabilitation as well. This particular study actually focused more on the evaluation of the wire puzzle task rather than the evaluation of the robot that was leading participants through that task. In the sports and exercise domain, this was an example of a Now robot being used as a cycling instructor, and the Pepper robot being used as a couch to 5 kilometer running coach. So definitely suggests that this kind of robotic system used to motivate people to do individual exercise is possible and would be a good thing. One thing that all of these studies that I pointed out here, there are loads more studies as well that I've missed off this list. But one thing that we want to focus on is the personalization aspect within these scenarios. So it's been suggested by this paper in particular, but lots of other papers as well, that personalization is key to getting that motivation and adherence to exercise over the long term, and both in terms of high-level personalization to groups of users and low-level adaptation to individuals over time, so the lifelong learning scenario. The majority of our work so far is focused on high-level personalization side of things. I won't go into too much detail about how we implemented the high-level personalization just because of time just now. But if you want to know more about it, the link to the paper is down the bottom. Essentially, we used a kind of learning from demonstration approach where we went out and we observed squash sessions and stroke rehabilitation sessions and kind of encoded what we had seen, encoded that knowledge into 12 different coaching policies. So we had 12 different coaching styles that our robotic system could then execute to provide coaching to people in both scenarios. In terms of the system itself, so we implemented it on the Pepper robot, and the robot can choose one of these 12 different coaching policies that we have based on the individual characteristics of the specific user. So things like the severity of the stroke or the squash playing ability of the user, the number of sessions, the motivation on that particular day. And using that policy that is chosen, it then selects appropriate actions given the state of the environment. These actions look something like this, lots of words there, but the easier way is probably just to show you a video of the system in action. So this is the squash coaching robot, and there's a very similar stroke rehabilitation coaching robot that we've made as well. So I'll let you watch the video.
Today, let's make sure that we shut and play. The father moves towards where you want the ball to go. Play another set of 30 back and prize, please. Remember, to stand and follow through towards the target. Extend and follow through. Nice. Good work.
So a little difficult to hear everything the robot was saying there. The acoustics, as it turns out, on a squash court play havoc with things. But you can see the general idea that the robot is providing coaching to someone during this individual practice session that they're doing. So what we expect is that choosing one of these 12 policies that's the best fit for each individual person will outperform just choosing a random one of these 12 policies or the baseline condition of just executing the session by yourself without any coaching. And in order to test this hypothesis, we're going to run two separate within subject studies, one with non-professional squash players, which we've actually completed and are analysing the results of just now, and then one with stroke survivors, which we're recruiting participants for just now, hoping to recruit around 16 participants for each study. And each participant will go through 3 different conditions. One, as I described, where the robot has selected the best fit of these 12 policies. One where the robot selects a random one of the other 11 policies that's not the best fit. And then a baseline condition where the person isn't receiving any coaching from the robot. So that's what we're doing at the moment. Our future work will be on the lifelong learning side. So looking at the low-level adaptation to individuals. And we're hoping to be able to use a similar method to Silva and Gombolay here, where we've done this section in terms of encoding domain knowledge into this initial policy. And then we're going to use that initial policy as a starting point for a reinforcement learning algorithm to further adapt over time. These are just a couple of examples of ways that we could potentially use reinforcement learning to personalize the interaction further. What we're doing is then plugging in that initial starting policy that we got from the high-level personalization into this reinforcement learning scenario. Thank you very much for listening. I'd just like to give a shout out to my funders, EPSRC, and happy to take any questions if we've got time.
Thanks, Marty, for the really interesting work and presentation. Do we have any question from you guys in the chat? We're a bit over time, but I think we have time for one question. I'll go ahead and just ask you right away in terms of, for sure, I think it sounds great to go in the direction of lifelong learning. So what do you think would be your main challenges when adapting, or, when, let's say, having your system account for lifelong learning? So learning over more sustained periods of time. What do you think would be one of the challenges there?
So I think one of the challenges is deciding on how we would kind of calculate the reward function. So would it be based on performance? Would it be based on engagement? Would it be based on enjoyment? All these things kind of affect the motivation of someone to do these exercises. So trying to decide what's going to be most important, or a combination of those things, I guess, to base the reward function off will be probably the biggest challenge, I would say.
Got it. Thanks. And again, we're over time, so I do have a few more questions for you, and maybe we take it offline in the chat and so on. So thanks again for presentation. And right now we have our second round of breakout sessions. So Aditi, are you going to divide us into different rooms?
Yes, I'm going to do that. So I'm going to open the breakout room. So if you were in one before, you should be joining the same room. For everyone else, I'll sort of put you back into the rooms that you were in before, and open a new room for those who have joined us since. And today we're going to just talk just for a few minutes, quick breakout session. We're going to talk about which robots from science fiction with adaptive capabilities we're most likely to have in reality in 5, 10, and 20 years. Why and what are we missing? So let me go ahead and open the rooms, and see you back here in a little bit.
Yes, all right. Well, thank you to everyone who's stuck with us throughout the day. And thank you also to our panelists who have arrived or are arriving. This is, I believe, our final activity of the workshop. It's the panel, so I'll just give a quick introduction to our panelists, and then we'll kick it off. We've got a lot of I think, interesting perspectives to hear about. So let's see, we've got Samuel Barrett, who's a senior research scientist at Sony AI. He got his PhD thesis at the University of Texas, Austin. And there he worked on ad hoc teamwork problems, cooperating with unknown teammates. And he was also on the winning team of the 2012 International RoboCup competition. We've got Ben. Is Ben on?
Yes. Hi.
Yes, there you are. Yes. We've got Ben Burstfield, who's a research scientist at Toyota Research Institute. He's the technical team lead for the Robot Lifelong Learning Project. And he got his PhD from Duke University. And then he was a postdoctoral researcher at Brown University. We also have Dr. Kate Darling, who's a research specialist at the MIT Media Lab. She's the author of The New Breed: What Our History with Animals Reveals About Our Future with Robots. And she has research interests in technology and society, the near-term effects of robotic technology, especially legal, social, and ethical issues. Kate has also run experiments, held workshops, and writes and speaks about interesting developments in advanced technology and intellectual property. We have Professor Kirsten Dottenham, the Canada 150 Research Chair in Intelligent Robotics at the University of Waterloo. She is a longtime member of the HRI community. I would say perhaps even a founding member of the HRI community. I mean, I remember reading papers from Professor Tottenham that, just kind of laid out where this whole field was going and why anyone should be interested in it back when it was really a crazy idea. So we're especially glad to have her with us today and hear her perspective on the field. And then Natasha Jacques is our last panelist. She'll be joining us shortly. And she is a senior research scientist at Google Brain and also a visiting postdoctoral scholar at UC Berkeley. Her research focuses on the use of social information in reinforcement learning in multi-agent and human AI interactions. She completed her PhD at MIT and has won a whole host of awards for her work that kind of melds the best of affective computing and interactive AI. So we are very excited to hear from them all today. And with that, I'll hand it off to Bahar to tee up the first questions.
Thanks, Sam. So it was very nice to see you all here. Thank you very much for coming. And I'm going to start us off with if you can give a brief introduction about your work, highlighting areas that contribute to lifelong learning or personalization, particularly for robots. And hi, Natasha, welcome in time. Okay, we can start with you, Natasha, while you're here.
Yeah, sorry I'm late. I'm actually just gave my job talk for a faculty interview, so it's a little hectic today. Thanks. Yeah, exactly. So my research is focused on both multi-agent reinforcement learning and human AI interaction, and thinking about how do we develop algorithms for learning effectively in both contexts, and how can we learn effectively from humans. And one big focus I've had there is, maybe we want to be able to detect signals that are rich and more ubiquitous in terms of interacting with humans, like their social signals, their facial expressions, the sentiment in the language that they're using, and how can we learn from that, especially with RL techniques. So, thanks.
Thank you. Thank you so much. Kirsten, can we go on with you?
Yeah, so
I think we lost your audio. We heard you say at the beginning, and it sounded like maybe a plug got unplugged or something.
Yeah, we can't hear you right now. While you figure that out, we can hear you. There we go.
Yeah. Okay. I just did the unplug plugin. So I'm very interested in how to make robots socially acceptable, in particular when it comes to some application areas of these robots. And personalization and learning is certainly one of the key aspects to it, because after all, if we want people to interact long-term with systems, then we need to go beyond the novelty effect. The systems need to remain interesting, I would say, and but also challenging when it comes to, let's say, therapeutic applications or rehabilitation applications. So that's why I was very interested in joining this panel today.
Perfect. Very happy to have you here. And I'll go with Kate next, if you want to.
Sure. Hi, everyone. Sorry about the sunglasses. I have an eye injury, but I'm also very cool. Just want you to know that. So I'm interested in HRI, both on the level of how people engage with robots, but also on kind of the broader societal level. So especially as we start putting robots more out into the wild and into shared spaces where they have more long-term interactions with people, I'm interested in what happens and how that fits into kind of existing systems of norms or ethics or behaviors or even laws. So for example, Sam mentioned I have a book out that I published last year, comes out in paperback next month. I'm not here to promote my book, but just as an example of the type of thing that I think about, the book does kind of a deep dive into the history of animal domestication and how we've used animals for work, weaponry, companionship, and what lessons we can learn from that when we're thinking about how to integrate robots. And the argument isn't that robots and animals are the same. The argument is that when we try on this different analogy, it changes some of the conversations that we are having as a society around things like robots and jobs or robots and social relationships. And it changes the conversations in, I think, pretty useful ways if we look at some of our history there. So I also think it's pretty important at this moment in time, again, with more robots currently entering into these shared spaces.
Absolutely. And with that, I'm going to hand it over to Sam for his introduction.
Yeah. So on my side, I'm interested in human and robot interactions from both my grad school work, where I did ad hoc teamwork, so trying to cooperate with teammates you don't know ahead of time. And if you imagine robots out in the world interacting with humans, you do need to adapt without negotiating what needs to happen very well. And so some of that adaptation is very interesting there. More recently at the startup Cogitai, we worked on some of the scaffolding of knowledge, try to build skills and provide tools for people to scaffold those to teach skills sort of sequentially and build upon existing skills to do things. And the most recent work I can talk about is at Sony AI. We've created the AI Sophie in the GT platform that on the GT game that beat some of the best human players at the game, but also thinking about the aspects of how to compete with the AIs and be good sportsmen, like exhibit good sportsmanship while competing in a complex game, and also looking at how to do things like integrate it into a game and deal with learning from people or being good opponents for them and like tailoring things to different human levels and that sort of adaptation.
Very interesting. So combined games and robots
Yep.
for lifelong learning. They're very nice. And finally, off to Ben.
Yeah, so our group has this kind of long-term vision. I think a lot of people share it, of robots in like people's houses, helping them, make dinner, helping them do chores. And well, there are many problems with doing this that aren't solved. But one of the big problems there is you really need to tailor your robot's behavior to the specific person that's interacting with it. If I'm making dinner and I want a robot to help chop my vegetables, they need to cut it the way that I want for the dish, not just like in a void. So my team, we take a skill-based approach generally. I think Sam had mentioned some of this stuff as well. But we think about how do we learn skills and how do we specifically add new skills to some existing repertoire. And then, if we have some set of skills and we want to accomplish a new task, how do we actually adapt those skills? They may need to change a little bit depending on the environment. There's a huge amount of variation in people's houses. And how do we learn when it's appropriate to execute various skills? When do we learn which skills can be sequenced together? So there is, I think, both an HRI and a lifelong learning component to a lot of that, although we call ourselves the lifelong learning group, but we really do some of each, I think.
Absolutely. Household chores are, I think that had a lot of people in roboticists go into the field for this, like to make the Rosie the robot from the Jetsons cartoon. So my next question is that what application areas do you see benefiting most from recent research and advances in lifelong learning and long-term personalization, and why? I'm going to start off with Sam, if you want to go ahead.
Yeah. I think there are a lot of application areas for lifelong learning. Definitely, it's hard to imagine any in-home robotics without it. Definitely, for sure. A lot of that you need to keep like everybody's home is different, and everybody wants things done differently, and so everything in that sort of space definitely makes sense. But I think also there's a lot of interesting space for this in in non-physical presence too. I know like we often focus on the robotic side, but I think there's a lot of things in terms of like agents that you interact with, in games or online or other things that could be very useful. You can imagine things like in a sort of library setting, you could have an assistant there that helps you find information and things like that. That like, I definitely think there's a lot of knowledge, like ways of how to interact with knowledge that you can definitely work on with agents that are very interesting. How to present that to people.
Absolutely. I think it was relating to Ben's topic as well. So I'm going to direct it to him now. Absolutely. Sorry.
Yeah. So, I mean, this isn't exactly an application specifically, but I do think that, the last 5 years especially has seen this sort of big explosion of kind of big data machine learning, where you have really large data sets and you can use a lot of increasingly powerful compute to do pretty amazing things. But there's these domains where you're never going to have a lot of data. Household robotics is one, but whenever you have basically enough distribution shift that you can't model it properly with your training data, it's hard to imagine how you do that properly without something like lifelong learning. And then I think the big missing piece there is knowledge distillation. Like a lot of us in robotics, we think about skills because it's an easy sort of human thing to write down to kind of give us these higher level primitives that we can use to distill knowledge, but it doesn't work for every task. So I think moving forward to, you know, a wider variety of settings, one of the keys will be, you know, what form should knowledge distillation take? Like, is it weights in a neural network? Is it, you know, we pick exemplars from data sets and keep those around? Like what really should that look like? And is there an application agnostic form it could take?
Absolutely. Actually, it's going to be my next question, but before that, I'm going to head it off to Kate for your answer.
Yeah, I mean, I can echo some of what's been said, which is that, I mean, obviously this is broader than just home robotics. I feel like in terms of people's expectations for what a robot is and can do, you know, everyone's very much influenced by science fiction and pop culture, not just when it comes to home robots. And it feels like sometimes the whole premise of robots is that they're personalized and can engage in lifelong learning. You know, some people wouldn't even call it a robot if it can't do that. So I'm having trouble thinking of application areas where it's not important.
Makes sense. Absolutely. It's our field, so we could all be saying we all need it everywhere, but of course, maybe not in the industrial setting, for instance. And
but people would call those just machines, right? Do people even call those robots unless they have?
It's a big discussion, you know, like people even call dishwasher a robot, and I'm like, no, not really. So yeah, it's a big topic. Natasha, what's your take on it?
Yeah, I think personalization is incredibly important. Like, I've actually seen this in my own work, thinking about just trying to predict people's emotions, right? If you want to do that, what we actually discovered is you really need personalized models because people will react in the exact opposite way to the same stimuli. So if you have a robot that's trying a certain policy for a way of interacting with a person, that's just not going to work universally. Like, you need to be able to adapt to the individual and to personalize if you want them to be satisfying. So.
Absolutely. And I remember, Kirsten, you had a paper back in the time, like comparing dogs and that we should have robots like dogs. So what are your take on what are the areas that we can have for personalized and lifelong learning in robotics?
Yeah, thank you for mentioning that paper. I was at some point wonder if anyone has read it at all. So I just wrote down that I definitely need to get Kate's book and read up on that. But in terms of application areas, I can't think of particular application areas where you know, you specifically would need personalization and lifelong learning. While I listened to the other speakers, I was even wondering, can I think of application areas where you do not need it at all? And the only thing, while I only had these few minutes to think about, is thinking about very short-term interaction. Let's say you have a robot and greeting people entering a restaurant, and all the robot does is just to say, welcome, please have a seat. Nothing else. I mean, just, you know, almost like an automaton, you know, it cannot say anything else. It is just, or maybe it has one or two more phrases, but then again, it would be about adaptation. It would have to know when to say certain phrases to certain customers, maybe in different languages. So yeah, it is quite difficult for me to think about applications where you do not need those skills. And I would still say you can call something a robot without having those skills. But at the end of the day, adaptation and learning, it is really, really key of sustaining social interaction and engagement. And this is why when back in the days I wrote this article also talking about dogs, this is why dogs have such a successful relationship with their owners. Not only that they can also carry out various tasks, but they are responsive. They can adapt to their owners. They can even adapt to their owners' moods and emotions. So I would still say you can have a robot without these skills, and I still put the label robot on it. But it is very difficult to think about any meaningful scenarios or applications without those skills.
And on that, so what do you think are the skills that we need for the fundamental aspects that we need for lifelong learning and personalization?
Sorry, are you asking?
Yeah,
me,
go ahead, Kirsten.
Okay,
go
okay,
to Natasha.
okay. Sorry, I was confused. I think one of the very interesting mechanisms that already has been mentioned, I think, by a couple of people, is this issue of teaching. I remember when we started research in 2004 on home companion robots, which many of you are also interested in. And one of the first things that we were talking about is that the robot needs to interact with people in a multimodal way, using sounds and motions and expressions and colors. But then we immediately started thinking about, how should the robot express those? What type of sounds? What type of colors? How should these colors be matched? And then we immediately realized it cannot be us just making those decisions, us as researchers a priori deciding, when the robot stops, it should be red, and when it's moving, it should be green, because there are always different interpretations. And so this is why we then also developed some mechanisms of where the users themselves could personalize the robot. So this didn't involve any learning on the side of the robot, but we then later in other projects then also went beyond that and said, well, actually the robot needs to learn these personalizations. And the most effective way we could think of is really that people teach the robot what to do. And then in several projects, we focused on human robot teaching, because again, leaving it up to the robot on its own, deciding on when does it need to learn, what does it need to learn, how does it need to learn, these are very, very hard problems. But people usually, if it's a particular application area like a home robot, if you ask people, they usually have quite clear ideas on what they want the robot to do, how they want it to do it, when they want it to do it, and what they don't want the robot to do. So this is why, I mean, personally, for me, human robot teaching is a very powerful mechanism for personalization and robot learning.
Absolutely. Natasha, would you like to go ahead?
Sure. I think in terms of abilities that these agents or these robots will need, like if we dive into the lifelong learning component for a second, I do think that's quite challenging, right? So a lot of our current, I work on reinforcement learning a lot as a tool, but most reinforcement learning algorithms are built on the assumption that the environment is non-stationary. So the payoff that you get for trying different actions doesn't change over time. But of course, with learning from humans, it's going to, right? Like, let's say, the classic example is just like, if I tell you a joke once, maybe you laugh, that looks like it's high payoff. If I tell you the same joke again, you're not going to laugh a second time, right? It's non-stationary. So how do we actually develop algorithms that are able to do this adaptation to this changing preferences of the human over time?
Do you have any approaches to do that?
Yeah, well, I mean, interestingly, even though theoretically this should be hard, in practice, it's not as hard as you might think. So if you use like on-policy reinforcement learning, and one of my favorite algorithms would be PPO, it actually tends to adapt pretty well. So, neural networks, we talk about them having catastrophic forgetting because previous experience with the world is erased by continual training in the environment. Maybe that's actually not a bad thing in the case of a non-stationary environment, because you can think of it more like plasticity. But I think it's still an open research question how to develop the right algorithms to do this in a good way.
Absolutely. And Ben, what's your take on this?
Yeah, so I think the things that were said so far definitely are true. I think also your abstraction is kind of a big missing piece here. Like a lot of times we talk about teaching a robot or learning from demonstration, but actually depending on what you're learning, that process can look very different, right? You could be trying to replay a trajectory and the problem is just mapping what the human does onto the robot, or you can be indicating a goal, or any of a whole number of things. And I think it's a little bit of a chicken and an egg problem, where if you have a bunch of examples of successful teaching, you can try to pull some sort of abstraction from there. And if you have a good abstraction, a lot of times teaching is very simple, where you say, okay, really like we're specifying a goal location here, and maybe it's a point in 3D space, right? But when you don't have either of those things, I think doing this in a general way is really hard. There's been some work in the last decade or two on automatically generating like grounded symbolic languages, right? PDDL is like a planning framework a lot of you are probably familiar with. And so people have done things where you say automatically try to generate symbols that are expressible with PDDL, and then you can plan over them. But there's still a lot of these really kind of handcrafted brittle assumptions that you'll make. Like you have some representation of your state space and you can do clustering to extract symbols, or some of these other things that in practice I think are very difficult when you're authoring like complicated robot systems.
Absolutely. This is complication is our job, right? For this thing, for all everyone here. And Sam Barrett, would you like to go ahead?
Yeah. I agree with a lot of things that have been said here already. I think one of the aspects that we maybe haven't touched on is that I think one of the important things for people to like be willing to work with robots and like to keep that patience is like the robot communication back too, which is like making sure it has some way of telling its intentions. And also like you want it to adapt quickly in some way. Like I know like maybe you won't get to what you want, but you want to be able to show that you're trying to learn and actually meet the person halfway, because people are really forgiving if they think you're trying and they think the thing is working. And anytime they think that their feedback is going into a black box, people give up really quickly. And so I think that's one of the interesting things is not just how do we make the robots better, robots or other agents better, but how do we make sure we communicate with the humans so that the humans are patient enough and keep giving guidance in the ways that help us too. So like also guiding them to give the right sort of guidance. If you can't take inputs in the way they're trying to do it, make sure you try to guide them to something that is more useful for you. So I think there's a lot of that side of it I think is particularly interesting.
Absolutely. I remember like back in an experiment I was doing, and people were so patient with the robot. They were really annoyed by the fact that the robot was not doing what they wanted to do, but they were also very patient and are trying again and again, like 7 minutes of trying the same question, even though it's the wrong question to ask. But they were really patient, and it's really nice that people are helping robots get better in that way. And finally, Kate, would you like to share your thoughts on this?
Sure. I mean, y'all work on these skills and I don't, but I would, echo Sam that one of the big hurdles that I see to these robots actually being used long term is people being willing to work with the robot, like you said, Sam. So like social acceptance, and particularly, I just see right now it's so interesting because right now we are seeing a lot of robots being deployed, and the engineers have worked so hard on getting it to work perfectly or like reasonably well and not disappoint people's expectations immediately. And then they put it out there and they forgot to consider that people have either a very negative or a very positive reaction to any robot they encounter. So people are either love or hate the thing for reasons that weren't really considered in the whole deployment process, and sometimes have to do with context. And so like Kirsten was saying about robots needing to be able to adapt to a context and being willing to learn from the context that they're put into or the humans that they're interacting with, that's really important, as well as just considering that the robot, as my friend Madeline Ellish likes to say, isn't being deployed so much as being integrated into an existing system and an existing social system that already has norms that really need to be considered in order to ensure that the robot is going to be successfully actually used and not just stuck in a closet somewhere.
Absolutely. I mean, that's the selling point is really important. And actually, I have a question right on that. So we've seen the rise and fall of personal robotics startups over the past years. Setting aside the cost of the robot, what are the key aspects necessary to make personal and adaptive robots that customers, whether it be end users or businesses, would want to buy? Would you go ahead, Kate, on this one?
Yeah, I think, gosh, I can't remember who first said this, but I've heard it a number of times. Like the social robots that we're seeing right now in the home are kind of like the Palm Pilots of home robots, because I think other than cost and other than people's expectations of what a robot can do being disappointed because they think we're much further along than we actually are. Other than that, I think that people haven't really understood the use case for some of the interactions that a robot can provide. So like, we were talking about a dog. People understand the use case for a dog, and like why it can be fun and interesting and valuable to have a dog, even if the dog is not performing a function like guarding your home, or your cat is not, chasing the mice out of your grain larder. People understand the utility of pets. People don't understand that for robots yet, but I think that they will. I think that it's just a matter of getting enough adoption or having enough of a use case that more people do engage with robots in their home. And I think that is going to be the tipping point.
So I'm going to direct it to Kirsten after that.
Yeah, one of the problems is that if you sell something as a robot, then it comes with a lot of baggage, as many people have discussed, people immediately have some mental models. They have some ideas in their mind of what they have read in books, seen on television, Netflix shows, and so on. And then the poor robot has to live up to these expectations, and these expectations might be positive or they might be negative. And at some point, given that people often have very high expectations, there comes the time where, although they might find the robot initially entertaining, then at some point they ask themselves, so what? I mean, Kate was mentioning these use cases. So beyond entertainment, the robot has to have certain added value. What can the robot bring that is interesting enough to keep you engaged for longer? And I mean, animals, pets are sentient beings. They are fundamentally different from robots. That you get something back. If you invest your emotions into a dog, you will get something back. You will get a lot back. Not without reason do people call dogs, man's best friend. So beyond any utility, there's a lot of benefit. And I think I would agree. Lots of robot companies also a few years ago shut down. I remember, I think it was around 2015. It was Jibo and Kuri and Cosmo and lots of these robots. And a lot of people wrote articles about it, analyzing it, saying, is it? And I mean, numerous explanations were given. Maybe they were overselling it initially, but maybe the robots were not ready. But also, I think it is because of this term robot and the expectations associated. I remember when Alexa came first on the market, which, as far as I know, has never been sold as a robot. And I thought that was pretty smart of Amazon not to call it a robot. And personally, I've not studied it, but I would suspect that maybe this is the reason why people actually like it. And it's quite popular because people just looked at this black cylinder and had very few expectations of what this can do. And then they interact with it, and then they learn, oh, it can play my favorite song. Well, my phone can do this too, but hey, it can also order pizza, or maybe it can tell jokes. And so they were developing a mental model of what Alexa is, rather than encountering the system already having some preconceived ideas of what the system should do or cannot, or can do or cannot do. So I think this has to do a lot with the introduction of these systems and the framing. And I thought at some point maybe we should stop using the word robot. But then I thought about, okay, what other word would I suggest? And then I couldn't come up with something convincing.
On a related, absolutely, on a related topic, I actually have a question to our industry experts. How much do you believe that the industry has contributed to or avoided in terms of these areas? Why do you think it has been the case? And what would you like to see the robotics industry to do create a leap in these areas? Start off with Ben.
Sure. Yeah. So I actually think that more is happening behind the scenes than is apparent. Someone earlier mentioned automation in warehouses as an example of where maybe you don't need lifelong learning. I would probably actually push back against that a little bit. I think there's increasing kind of awareness that reconfiguring, your warehouse or reconfiguring your assembly line, doing all of these things, it's really labor intensive. And so that I think has been the Trojan horse for some of these industrial groups that maybe don't have the patience for a really long time horizon. Thierry, we're a little bit divorced from that because we're more of a pure research organization. But talking to folks that are a little bit closer to the applied side, it's where people have gotten a lot of their first taste of some of the lifelong learning stuff. Even things like learning manipulation strategies for interestingly shaped inventory items. Like if you have a simple pick and place system that's sorting stuff, occasionally you have new items and you need to adapt to that. So I do think industry isn't currently focused as much on the bigger picture because it's longer time horizon, but there's bits and pieces of it that are starting to kind of break into it.
I think that might be also cost dependent as well, because like short-term revenue is more important than the long-term, the big picture of the robotics industry.
Yeah, although there's enough money on the line, Amazon, for instance, with their picking challenge and some of their warehouse stuff, that there's maybe a little bit more patience for some of the like medium term stuff with warehouses, just because the payoff is so huge.
Absolutely. And Sam, would you like to continue?
Yeah, I'm not sure how much I have to add on this specifically, but I'll do what I can. But my feeling is that it's a mixed bag in industry for some of this, because as Ben was saying, like some of this research is farther out, and getting industry to care about farther out research is sometimes difficult. Like sometimes you can do it, but it requires the right scenario. But I think a lot of the interesting things is also trying to find the shorter term use cases of some of these, like as Ben was saying about in warehouses and things like that. I think that I guess one of the reasons I'm at Sony AI is that I think one of the areas is pushing that in things like games, where you don't have to necessarily push the entire, like you can add on to an existing product in some ways. Like people are already interacting with these. And I think that's one of the interesting ways you can get into this with industry is it doesn't have to be a new product all on its own. Like I think like Jibo is hard to do well and making a new product, but if there's something that's already in your house, already you're interacting with, I think there's a lot of stepping stones that people can do. As Kirsten was saying, talking about like getting Alexa in people's houses, like there were some basic things that it could do that people are like, oh, I want to be able to set a timer while my hands are full in the kitchen. Like that's the sort of thing that you think it can do, but then you get your foot in the door and maybe you can slowly add features to that are then useful. So I think there's something to that where you keep people's expectations low, as Kirsten was saying, with trying to make sure people don't sell too much, but then actually pushing incremental improvements on some of these things that do actually lead to some of the big changes over the long run. But I think I do agree that the managing expectations is a huge part of this, and trying to make new products in particular is hard for that. But adding on to products, I think, is at least one stepping stone.
I think so as well. I think we should just all collaboratively come up with a new name for Robo, so we can put it into the to user sense, and then just when we have it ready, we can call it Robo. And Natasha, would you like to continue?
Sure. Maybe just I agree with what everyone is saying, but just to add on, I do think, for example, Google, just to be a bit of a Google booster, forgive me, but it is contributing to fundamental robotics research. They've got the arm farm. They're trying many different manipulation tactics on that. They've got either trying to make a robot that can sort trash from recyclables in a cafe and pick them up and stuff like that. So I think there is still a role for the research arm of big companies to contribute to fundamental robotics research.
Absolutely. And I will go on with, we're going to come back to the audience questions. I see a raise hand. But for privacy. So we have lifelong learning, we have the data storage, and you're using that data, and it's, of course, privacy is an issue. And of course, there's an ethics issue as well, because we might be using it for building relationships with people. We're being in a sort of manipulative way to our behaviors on how the people perceive us. So what are your suggestions on this topic? Kate, I'll start off with you.
Oh yeah, how much time do we have? So yeah, I've always been obsessed with, the HRI subfield of persuasive robotics, and like showing how you can change people's behaviors or change people's beliefs through interaction with a robot, particularly with a social robot. And we're always told that that's for the user's benefit, and it often is in the applications that we're seeing in research. But, as people develop these robots against the backdrop of corporate capitalism and short-term profit incentives, we're going to see that being used by, the billion-dollar advertising industry, et cetera, et cetera. So it is, I was just yesterday reading about some of the policy things that need to change in this area. I think that basically we need to be aware of this on every level, right? I think designers of these technologies should only collect whatever data is necessary for whatever function they're trying to create. I think there needs to be more education and awareness among people building the technology. I think there has to be policy in place that's setting the right incentives for companies that are on the market. I think there's a lot of stuff that needs to happen. One of the interesting things that one of the students in our lab just discovered is that a common proposed solution for some of this stuff is just educate people better, educate kids on how robots work and collect data, educate, consumers so that they know not to get manipulated. And it became very clear through her research that that may not actually do anything at all, and that people will still, so she was doing this with middle schoolers. It was a longer term study in the home. And this was Daniela Di Paola, by the way, a student in Cynthia Brazil's group. And she found that educating kids on how a robot works has no bearing on how they interact with a robot, how much they trust a robot. And I would suspect that it's, maybe not quite the same, but similar for grown-ups as well. So there's a lot to be done. Some of the solutions that I'm seeing being thrown out in the policy world or education world, like transparency, just like aren't enough in this world. And we need to be looking at some of the similarities between how social robots as a persuasive technology can persuade people, and then comparing that not to like television advertisements, which is what all of our like children advertising policies are based on, but comparing it to things like influencer marketing, multi-level marketing schemes, more of these social persuasiveness, person-to-person methodologies, and looking at the ethical issues and how we can address them there.
Absolutely, you basically covered the whole area, but I'm also going to ask Kirsten what is her take on the approaches for privacy and ethics in lifelong learning and personalization.
Well, it's huge. I don't have any solution. No one has. Certain things can be done. I'm not so much worried necessarily about the robots today, because, for example, in my own home, I don't have any robots. I'm more concerned about what this thing here knows about me, my phone. And when I got that one, I spent literally hours trying to switch off certain settings that were default settings that I didn't want. And it was not easy to do that. And when I ask people who have more experience with smartphones, who had already used them for several years, because I thought, okay, maybe I'm just new to it, but they confirmed that even they have problems still doing these type of things. I sometimes wonder if this almost oblivious attitude that we have to how much, how much is known about what we do, what we buy, what we are interested in, comes because information, digital information, is not visible unless you decide to make it visible. Let's say, if I drive a few hours north here, I could actually, if I go for a walk in Canada, encounter a bear. As soon as I see that danger, the potential danger, if I'm not behaving the way I should, then I know what the consequences would be. I see it. If I have to cross a road in busy traffic, I see the cars, I see the situations. The danger is in front of me. The problem, I sometimes think, is that people just do not worry what their smartphones collect, is that they cannot see it. They know intellectually, oh yeah, sure, everyone says they collect lots of information. Yes, they collect lots of information. Maybe they shouldn't do it, but it doesn't have any emotional grounding. There is no, grounding in real life experiences, different from when I cross a road or when I encounter a grizzly bear somewhere in the woods. So, I mean, robots, as far as I'm concerned, are just another piece of digital technology, and the same dangers and opportunities also, but also dangers are associated with them. So with robots, given what some research studies show, people might even more overtrust them. So it makes the situation worse. And do I have a solution to that? No, I don't think, anyone really has it. We need to consider this really, really carefully. And I sometimes wonder, how can we make these dangers visible, more grounding it in real life experiences, so that people can make an informed decision. Because as I said, there is a difference between what we know intellectually and how we make decisions, which is also very much based on our personal and emotional experiences. And this is lacking because digital information is not visible. It's something that people talk about, but we don't see it unless someone decides to actually visualize it. So this is my take on that.
How about if we keep the information on the robot only?
Yeah,
No cloud computing.
In our current research here in the lab, this is what we do. That's why we also often don't use cloud services for speech recognition or so, because we want to keep it local. We want to keep it contained. But of course, for certain applications, for certain systems, you might have other approaches. You cannot always do that. You cannot always keep it local. I sometimes think really people need to be informed also better, although Kate suspected maybe education itself doesn't really help, but certainly these terms and conditions that you quickly click on, this doesn't work, it doesn't fly. There has to be more than, oh, please read first spend 5 hours reading our terms and conditions and then click accept. So I never read them, I just click accept. I don't have time, I don't have 5 hours to read all of that stuff. So but somehow we need to find a way to make people more aware of that. And when I say people, I mean myself also. I need to be careful. I'm maybe a little bit more conscious about it than some other people, but still, I need to always ask myself, okay, when it comes to my laptop or my mobile phone, what are the settings? When I'm using a browser, I need to check, I have to go into the menus, and which again, it takes time. This is a big obstacle, that it's so time consuming to learn about how the system is being set.
It's really hard, just to jump in very briefly, because also people, even if they know perfectly how it works and they're against it, they'll still trade their data for the functionality. So, I might not like that Alexa is recording everything I'm saying right now, but I can order diapers hands-free. And so people will trade their privacy. So we need more than just addressing this on the individual level.
I think also, everything Kirsten and Kate said, I thought was great. Fundamentally, in some ways, there are two issues, actually. I think Kirsten talked very well about the sort of data issue and the privacy issue, but actually, Kate, to your original point, which is that these agents now are basically inducing changes in behavior, right? And as robots get more general purpose and become more tightly integrated in people's lives, like that potential will only grow. You know, Instagram already, people are having debates about how it changes, you know, development or people's behavior. Now you're 24/7 living with a home robot. And I think that's where lifelong learning offers both risk, but also maybe the potential of a solution, right? So right now, part of the issue is that every problem we're solving with machine learning is so narrow. So, you know, you have an advertising agent and its goal is to maximize click-through rate or ad revenue or something like that. And similarly, like with robots, you know, if I tell a robot, all right, the goal is that you need to chop these onions into a certain shape, maybe I'll give it some constraints over its actions, but it's not thinking at all about other things I would like please don't put holes in my counters and these other things. And eventually we shouldn't be solving problems from scratch. I think that's the dream of lifelong learning. Like you bootstrap everything from other experience. And part of that, I think, is capturing this really rich prior over like ubiquitous goals that people have, right? So I want my home assistant robot to maybe help me eat more vegetables, but not by, you know, guilt shaming me into it where I'm miserable and stressed out, but it's like convince me that I'm eating more because I think I'm going to die if I don't, right? And I think it's hard to write down what all of these things are. I don't really see an alternative other than we need to kind of learn it from a large amount of data over time and then incorporate it into every new thing that our robots do.
Yeah, if I can just add on to that, I really agree with that, because even if you say use federated learning to keep all the data on the device, on the robot, so the data isn't leaving the robot, I still am very scared of devices that are optimizing, you know, for my attention, let's say, or for the wrong metric, right? Like I don't want to constantly be having to fight adversarial and optimization algorithm that's trying to distract me or get me to do something or manipulate me. And so I don't know if this is popular in this crowd, but I actually really enjoyed like Stuart Russell's book, Human Compatible, where he talks a lot about, you know, if you have a short-sighted optimization algorithm optimizing the wrong metric, like we've seen like YouTube optimizing for watch time, there can be very bad consequences of that. So what should you be doing? Maybe you should be trying to infer the person's preferences online in a lifelong way, constantly adapting, but still have some uncertainty over those preferences. And, you know, maybe there are some interesting algorithms we could think about that would do that. But yeah, I think it's a really rich question.
I absolutely agree. All these points, they're absolutely gold. Now I'm going to hand the floor to Sam so we can take out the audience questions.
Yes, hi. Yeah, so we've had a number of good questions come in over the course of this panel. This has been a wide-ranging and really interesting discussion. So thank you all for being such active participants. I'm just going to go in order because I think we have enough time to cover all of the questions that have been asked here. So here from Maria Pinto, she asks, what would be the best tips to carry out a long-term interaction? What do you think are the most significant difficulties to carrying out this type of relationship? Does anyone feel moved to jump in and give an answer to that question?
Yeah, maybe I could start. I mean, if long-term means, you know, 24/7 home robot in your house, how can we build such a system that's interesting enough for people not to call the research lab after 2 days and say, okay, tried it out, I'm not done with it. Can you take it back? It just takes up space here in my house. I mean, for me, this is still, you know, extremely difficult. And, you know, despite then, you know, maybe abilities of the robot to learn, but we first need to make sure people keep the robot long enough in their house and tolerate it long enough so that it can learn and interact with the robot long enough. What if people don't really want to interact with the robot much, apart from maybe half an hour in the day, because otherwise they're just happy doing what they're doing. So I think there are these challenges, and still, how can we create these systems that are interesting but also safe enough? If it's a small toy robot, yes, of course, you can put it into someone's home, you know, but if it's a more substantial mobile manipulator, for example, then you need to also make sure that it is safe. It doesn't need supervision by researchers. So long-term studies are still very, very difficult. They also take time. They take resources. It is not something the student can easily publish 3 conference papers and 1 journal papers each year. If planning, carrying out, recruiting for the long-term study already takes half of the PhD or 2/3 of the time of a PhD. So this is also something, I mean, I as a supervisor also need to consider this. I cannot just say, oh yeah, it's from a research point of view, it's fantastic. Let's go long-term, really 2 years, you know, the robots in the house for 2 years. And then
so you're thinking like structural incentives that sort of disincentivize people from taking on long-term projects, right?
Because I mean, I cannot suggest a project where the student only after 4 years will have 1 or 2 papers coming out of it. That would not be very responsible of me, even if I'm really interested in doing such research. But then I have to find other ways to carry that out. But not with graduate students, you know, master students, 2-year master students, or 4-year PhD students.
From Isabel Schwaninger, she wrote in about this topic of the term robot and mentioned using the term latest invention instead to focus on people's daily needs and routines and try to sidestep some of the preconceptions that people have about robots. I like that term because I think it makes the connection more directly to some of these quite successful consumer products that we mentioned, which people do, you know, have in their homes and interact with for years. So it sort of, you know, suggests that it could be like one of those products as opposed to like the robots of science fiction. I'm curious, what do people think about latest invention as a term?
I mean, I think it seems pretty good. You know, the other adjective I've heard is smart. I think for a lot of people, like smart homes or home automation is maybe their first interaction with a physical system that can actually like affect their surroundings. So that may also be a way that sets expectations a little bit better, where it does several specific things. It's not a general purpose machine yet.
Isabel, I see you actually, you're on the video chat. Did you want to ask a follow-up question on top of that?
Yeah, it was. I just thought it was interesting that you were saying the term robot has this expectation and that it's when people start engaging with robots. And for me, it was actually one of the challenges that I identified in the participatory design process. So because you don't want to skew people's expectations in the beginning, and when you recruit them, for example, they have certain expectations already. So it's hard for them to focus on what might actually support them in their daily home and so that's how I explored expectations. I would explore the terminologies. I just thought it, maybe you have some perspective on this to share. When is a good time to actually introduce the term robot, or if at all, or maybe just leave it up to the people how they want to call the device or whatever. Also in terms of developing a solution, because it doesn't have to be a robot, it can be also something else that they want them to support. I'm working with older adults personally, so
maybe I can comment on that. I mean, one way to go is also to make it just very, very specific. You know, if I mean, Roomba is a vacuum cleaning robot, you could call it. This is an automated vacuum cleaner, which, you know, is, I think, precise enough. It doesn't have to be called robot. Or if you have a robot that can help you in the kitchen cooking, then this could be an automated cooking machine or something like that. I mean, I don't know, but yeah, my point is just maybe we should get away from this big class of robots, because anyway, the cobots will have in an industrial context are different from the pet robots we have that play with children or that assist older adults in a care home. So these are anyway different species, if you like. You know, it's I mean, if you talk about, you know, animals are insects and butterflies and birds and rabbits and humans and primates. And normally you do not just talk about animals. You know, you talk about, you know, there are birds in my garden, or I have a cat as a pet. we are specific, and maybe it's a good idea to be specific. I don't know.
Great. On that note, I would actually like to wrap up the panel. And thank you all to our panelists for participating and for these great responses. It was amazing. I loved them, and I hope our participants did as well. And thank you for your time. And I'd like to also thank our keynotes and accepted paper speakers for their amazing presentations, and our sponsors for making this this amazing workshop possible, the UKR Engineering and Physical Science Research Sciences and MIT Media Lab, Avinox Incorporation, Venn Robotics, and IBM Data and AI. And last but not least, my co-organizers have been amazing as usual. Thank you, Aditi, Sam, Herman, Hatice. If you're here, turn your video on, please. We'd like to say hi to you. And thank you for a wonderful collaboration. And thank you all very much for participating. We hope you enjoyed the workshop, and we hope to see you around HRI and maybe at the 3rd edition of this workshop next year for future discussions on these topics. Take care and stay safe. Thank you very much.
Yeah.